Space, the ultimate frontier of human exploration and scientific discovery. For centuries, we've gazed at the stars, asking questions about our place in the universe. Today, advanced technology and groundbreaking research are finally providing answers, but with each discovery come new, deeper mysteries. Join us as we delve into some of the biggest and most terrifying mysteries in the universe. The mysterious hexagonal storm at Saturn's North Pole has fascinated scientists since it was first discovered by the Voyager spacecraft in the 1980s. This intriguing weather phenomenon spans approximately 20,000 miles, dwarfing many of Earth's largest storms. Initially, its geometric precision seemed almost too perfect to be natural, prompting a series of theoretical investigations and lofty speculations. After years of study, researchers now believe that the hexagon is formed by atmospheric phenomena specific to Saturn's unique conditions. The jet streams in Saturn's atmosphere circulate with such incredible speed and over such vast distances that they create standing wave patterns. These waves form tight geometric shapes rather than the more amorphous storm formations seen on Earth. One key factor in the hexagon's formation is a phenomenon known as Rossby waves. On Earth, these waves influence large-scale weather patterns and ocean currents, but on Saturn, their behavior is magnified. Saturn's gaseous composition and lower density allow these waves to interact across greater distances with less friction. Essentially, the jet stream at Saturn's North Pole rotates at about 200 miles per hour, leading to the development of stabilizing forces that structure the gases into a hexagon. Additionally, temperature variations play a role. The interior of the hexagon is warmer compared to its periphery, causing shifts in atmospheric pressure that help maintain its rigid boundaries. Thus, combining high-speed jet streams, fascinating planetary wave interactions, and temperature gradients results in the stunning hexagonal storm that continuously mesmerizes scientists and stargazers alike. Venus is an enigmatic neighbor in our solar system, not least because of its peculiar rotation. Unlike most planets which spin from west to east, Venus rotates from east to west, completing one turn every 243 Earth days. This retrograde rotation, as it is called, intrigues scientists who seek to understand its origins. The leading hypothesis suggests that Venus may have experienced several significant, colossal impacts during its early formation period. These cataclysmic collisions could have supplied sufficient force to alter the planet's rotational direction and speed drastically. Given the chaotic early solar system, where violent impacts were frequent, this explanation holds considerable weight. Moreover, tidal interactions with the Sun further complicate this slow, backward spin. Venus's incredibly thick atmosphere, which is primarily composed of carbon dioxide, creates severe atmospheric tides. These tides interact with the planet's surface to generate frictional forces that could gradually affect its rotation. Over billions of years, such interactions may have resulted in the alteration of Venus's spin to its current retrograde state. Additionally, computer models simulating the planet's dynamics also suggest that gravitational interactions with the Sun might have played a cumulative role. Thus, a combination of colossal impacts in its youth and ongoing atmospheric and gravitational interactions appears to have conspired to make Venus the slow-spinning, backward-rotating planet that it is today. Jupiter's upper atmosphere is astonishingly hot, clocking in at temperatures around 900 degrees Fahrenheit, much hotter than anticipated for a planet situated nearly 500 million miles from the Sun. For decades, this perplexing conundrum has puzzled scientists, as conventional wisdom would suggest that such distant solar radiation should produce significantly cooler atmospheric conditions. Recent research, however, offers intriguing insights into the mechanisms behind this unexpected heat. The answer lies primarily in the planet's powerful auroras. Jupiter's magnetic field is exceptionally strong, about 20,000 times more powerful than Earth's. This magnetic field creates intense auroras, similar to the northern and southern lights on Earth, when charged particles from the Sun slam into the planet's atmosphere. These auroras are not just dazzling light shows, they generate significant amounts of heat. High-energy particles precipitate into the atmosphere, transferring their kinetic energy into thermal energy. This process heats the upper layers of the atmosphere to the extreme temperatures observed. Moreover, the rapid rotation of Jupiter, completing a full spin roughly every 10 hours, helps to distribute this heat more effectively around the planet. In addition to auroras, there are other contributing factors. Studies indicate that gravity waves, which are ripples in the atmosphere created by turbulent airflows, might also play a role in distributing heat from the lower layers up to the upper atmosphere. These waves break and dissipate energy high above Jupiter's cloud tops, adding further warmth. Thus, the confluence of dramatic auroral heating and the action of gravity waves working in concert reveal a complex yet captivating explanation behind Jupiter's unexpectedly sizzling upper atmosphere. Uranus, uniquely tilted at an angle of about 98 degrees, presents a rare and puzzling configuration among the planets in our solar system. Unlike the near-vertical rotations of most planets, Uranus essentially rolls on its side as it orbits the Sun. The most compelling hypothesis to explain this unusual axial tilt involves cataclysmic collisions. In its formative years, Uranus likely encountered one or more massive impacts with celestial bodies. These collisions, especially if they occurred at oblique angles, could have imparted sufficient angular momentum to tilt the planet dramatically. The leading theory posits that a protoplanetary object roughly the size of Earth collided with Uranus, causing the planet to tip over. The consequences of such a colossal impact would be profound, affecting not only the planet's tilt but also its internal structure and atmospheric dynamics. The collision might have generated enough heat to significantly alter Uranus's core and mantle, thereby influencing its magnetic field, which is off-centered and tilted relative to its rotational axis. This impact hypothesis is further supported by computer simulations and models which replicate the observed tilt and corroborate the plausibility of such an immense event reshaping the planet's orientation. The tilted configuration also leads to some uniquely fascinating seasonal variations on Uranus. Because of its extreme tilt, each pole gets around 42 years of continuous sunlight, followed by 42 years of darkness as the planet completes its 84-year orbit around the Sun. This prolonged exposure and deprivation create complex and often severe atmospheric phenomena. Thus, the dramatic tilt of Uranus, most likely the result of ancient cosmic collisions, gives rise to a planet characterized by its distinctive axial orientation and extraordinary seasonal cycles. The enigmatic spokes observed in Saturn's rings have intrigued scientists ever since the Voyager spacecraft first spotted them in the 1980s. These radial features appear as dark streaks and seem to move and change over time, defying initial expectations of the rings being purely static structures. Recent investigations, especially those conducted by the Cassini spacecraft, have provided valuable insights into the formation and behavior of these curious spokes. It appears that they result from complex interactions between Saturn's magnetic field and the particles in its rings. These particles are predominantly composed of water ice, but they interact with the magnetosphere in intriguing ways. The prevailing theory is that micron-sized icy particles within the rings become electrically charged by ultraviolet sunlight or by frictional interactions among themselves. When these particles are exposed to Saturn's strong magnetic field, they become suspended above the ring's plane. The magnetic field tugs on these charged particles, lifting them out of their typical ring orbits and aligning them along magnetic field lines, thereby creating the spoke-like features. This process is similar to the way iron filings align along the lines of a magnetic field in a classroom experiment, but on a far grander scale. Another interesting aspect of the spokes is their seasonal nature relating to Saturn's orbit around the Sun. The spokes are most prominent during the planet's equinoxes, when the rings are edge-on to the Sun. During these times, the increased solar activity likely enhances the charging of ring particles, making spoke formation more pronounced. As the angle of sunlight changes with Saturn's seasons, the visibility and frequency of these spokes fluctuate. Thus, the transient, ghostly spokes of Saturn's rings arise from a remarkable interplay of solar radiation, ring particle dynamics, and the planet's imposing magnetic field, together generating one of the most strikingly beautiful phenomena in our solar system. Mercury, the smallest planet in our solar system, has an intriguingly large iron core, comprising about 85% of its radius. This oversized core presents a fascinating puzzle to planetary scientists, who have developed several leading hypotheses to explain its unusual structure. Initially, it was believed that Mercury's proximity to the Sun played a crucial role in its formation. High temperatures close to the Sun would have caused lighter, more volatile materials to evaporate or be blasted away by solar winds during the planet's early formation, leaving behind a denser, metal-rich body. However, this evaporation hypothesis alone doesn't fully account for the immense size of Mercury's core. To better understand this disparity, scientists have increasingly considered catastrophic impacts as major influencing factors. One prominent theory suggests that during the chaotic early days of the solar system, Mercury may have experienced one or more gigantic collisions with other protoplanetary objects. Such impact events could have stripped away much of the lighter silicate mantle material, leaving a predominantly iron-rich core behind. Computer simulations have shown that a head-on collision with a body about 1/6 the mass of Mercury could produce a planet with the observed core-to-mantle ratio. Adding to this complexity, recent studies analyzing Mercury's magnetic field provide supporting evidence for these theories. The strength and behavior of Mercury's magnetic field suggest vigorous core dynamics, consistent with a large molten iron core. Thus, the oversized core of Mercury likely results from a combination of factors involving its proximity to the Sun and cataclysmic impacts that reshaped its internal structure. This remarkable planetary anatomy continues to offer deep insights into the early solar system's violent and dynamic processes. Mars' two small, oddly shaped moons, Phobos and Deimos, have sparked considerable debate and fascination among astronomers since their discovery in the 19th century. Unlike Earth's relatively large and spherical moon, Phobos and Deimos are irregular, lumpy, and much smaller, with Phobos measuring about 14 miles in diameter and Deimos roughly 8 miles. Their peculiar shapes and sizes have led scientists to two primary hypotheses regarding their origins. The first hypothesis posits that Phobos and Deimos are captured asteroids from the asteroid belt, located between Mars and Jupiter. These moons bear a striking resemblance to a class of dark, carbon-rich asteroids known as C-type asteroids, which are abundant in that region. According to this theory, gravitational interactions and collisions could have ejected these asteroids from the belt, sending them careening toward Mars. Once in proximity to the red planet, Mars's gravity would have captured them, locking them into orbit. This capture event would account for their irregular shapes and the fact that they do not share the same origin as Mars itself. The second hypothesis suggests that Phobos and Deimos may have formed from debris resulting from a colossal impact on Mars. In this scenario, a massive body, perhaps a comet or a large asteroid, collided with Mars, ejecting a significant amount of debris into space. Over time, this debris could have coalesced to form the two moons. This theory gains some traction from computer simulations that support the feasibility of such an impact event, generating moons with the observed characteristics of Phobos and Deimos. Additionally, this hypothesis aligns with the surface features of the moons, which resemble fragmented rubble pile structures. Recent missions and ongoing observations continue to deepen our understanding of these enigmatic satellites. For instance, Japan's Martian Moons Exploration (MMX) mission, aimed at landing on Phobos, will bring back samples that could shed light on their composition and, by extension, their origins. Whether they are captured asteroids or the remnants of a cataclysmic impact, Phobos and Deimos remain as captivating symbols of Mars's dynamic history and the broader complexities of our solar system. Pluto's iconic heart-shaped region, known as Tombaugh Regio, captured global attention when the New Horizons spacecraft sent back the first detailed images in 2015. Named in honor of Clyde Tombaugh, the astronomer who discovered Pluto in 1930, this region has proven to be more than just a captivating visual. It's a window into the dwarf planet's geological and atmospheric processes. The left lobe of this heart, known as Sputnik Planitia, is a vast icy plain primarily composed of nitrogen, methane, and carbon monoxide ices. This area is believed to be a gigantic impact basin formed by a colossal collision early in Pluto's history. The impact that created this basin likely occurred billions of years ago, and it was sufficiently powerful to carve out a substantial depression on Pluto's surface. Over time, cryovolcanism and the accumulation of these volatile ices have partially filled this basin, leading to the smooth reflective surface we see today. The nitrogen ice within Sputnik Planitia is particularly susceptible to sublimation and deposition, which drives active surface renewal. It is reworked by a process similar to convection currents in Earth's mantle, where the nitrogen ice warms, rises, cools, and then sinks again. This continual movement creates the polygonal patterns observed in the region and evidences a dynamic interior. Adding another layer of complexity, models suggest that Sputnik Planitia may play a role in balancing Pluto's orientation. The basin's location near Pluto's equator suggests its mass could have influenced the planet's spin axis, contributing to its current orientation. Active geological processes, a product of internal heat possibly from radioactive decay, also support the ongoing reshaping of Tombao Regio. The captivating heart-shaped feature therefore represents a confluence of impactful ancient events and ongoing dynamic processes, making it one of the most geologically interesting terrains in our solar system. Neptune's largest moon, Triton, presents one of the most intriguing and dynamic surfaces in the solar system, characterized by the presence of active geysers. These geysers, discovered by the Voyager 2 spacecraft in 1989, spew plumes of nitrogen gas mixed with dark, carbon-rich compounds several miles into Triton's thin atmosphere. The driving force behind these geysers lies in the moon's unique combination of cryovolcanism and solar heating. Triton's surface is coated with a layer of volatile ices, predominantly nitrogen due to the extremely cold temperatures, averaging around -391 degrees Fahrenheit. Beneath this icy crust lies a mix of other ices and possibly a subsurface ocean. The geysers are believed to be driven by seasonal heating from the distant sun, despite its minimal intensity at Triton's orbit, approximately 2.7 billion miles from Earth. During Triton's summer, sunlight penetrates this thin nitrogen ice layer, warming the darker material below. This trapped energy causes the sublimation of nitrogen ice directly into gas, increasing the pressure beneath the surface. Once the pressure builds up sufficiently, it finds weak spots or fractures in the ice crust, erupting as geysers and carrying entrained dark particles along with it. This explanation is supported by observations showing that the geysers are primarily located in the sunlit regions of Triton's southern hemisphere, where solar heating is most effective. The plumes can reach heights of up to 5 miles and are carried downwind by Triton's winds, forming dark streaks across the surface. These geysers are not only a captivating spectacle, but also suggest that Triton remains geologically active, driven by complex interactions between its surface and the limited but critical solar energy it receives. Intriguingly, the energy needed for these eruptions indicates that even in the cold recesses of the outer solar system, dynamic processes akin to volcanic activity on Earth, albeit at a much lower temperature, continue to shape the landscape. Triton's geysers provide essential clues regarding the moon's composition and internal structure, indicating the presence of both volatile ices and potentially liquid reservoirs beneath its crust, thus making it a focal point for scientific interest and speculation about extraterrestrial geologic activity. The Sun's corona, the outermost layer of its atmosphere, has long puzzled scientists due to its incredibly high temperatures, which soar to about 1 to 3 million degrees Fahrenheit. In stark contrast, the surface of the Sun, or the photosphere, is relatively cooler at approximately 10,000 degrees Fahrenheit. This counterintuitive phenomenon, where the outer layer is significantly hotter than the inner layer, is often referred to as the coronal heating problem. Decades of research and observations have shed light on several key mechanisms that together might explain this disparity. One prominent theory involves magnetic reconnection. The Sun's magnetic field is highly dynamic and complex, constantly being twisted and tangled by the motion of the solar plasma. When these magnetic field lines twist and snap, they release tremendous amounts of energy, which can heat the surrounding plasma to extremely high temperatures. This magnetic reconnection can create explosive events such as solar flares and contribute to the overall heating of the corona. Essentially, this process acts like a cosmic rubber band being snapped, where the stored magnetic energy is suddenly converted into heat. Another vital mechanism is wave heating, involving two types of waves: acoustic waves and Alphen waves. Alpha waves are generated by the turbulent motions in the Sun's convection zone and travel along magnetic field lines into the corona. These waves are capable of carrying significant energy from the Sun's interior to its outer atmosphere. As the waves propagate, they can dissipate this energy in the form of heat, much like how ocean waves crashing onto a shore release their energy onto the sand. Acoustic waves, which are pressure waves generated by turbulence within the Sun, can also contribute, though their role is thought to be less significant compared to alpha waves. These combined processes, magnetic reconnection and wave heating, present a compelling explanation for the high temperatures of the Sun's corona. Yet the precise details and contributions of each mechanism remain active areas of research. The Sun's dynamic magnetic field and the behavior of plasma within it provide a natural laboratory for studying extreme physics, offering insights that extend far beyond our star to other stellar phenomena in the universe. The quest to find Earth-like planets in the universe has intensified over the past few decades, driven by advancements in space telescopes and observational techniques. As we gather more data, it becomes increasingly clear that Earth-like planets might be more common than we once thought. One pivotal player in this search has been the Kepler Space Telescope, which, during its mission from 2009 to 2018, identified thousands of exoplanets. Based on its findings, it is estimated that there could be as many as 40 billion Earth-sized planets orbiting within the habitable zones of Sun-like and red dwarf stars in the Milky Way galaxy alone. The habitable zone, often referred to as the Goldilocks zone, is the region around a star where conditions might be just right for liquid water to exist, neither too hot nor too cold. This criterion is crucial because liquid water is considered essential for life as we know it. Kepler's observations revealed a surprising abundance of potentially habitable planets, suggesting that our galaxy may be teeming with worlds that could, in theory, support life. These exoplanets vary widely in their characteristics, from rocky terrains similar to Earth's to water worlds and planets with thick atmospheres, each offering unique environments that could foster different forms of life. Furthermore, studies using data from the Transiting Exoplanet Survey satellite, TESS, launched in 2018, and the upcoming James Webb Space Telescope promise to deepen our understanding. TESS aims to survey the nearest and brightest stars, potentially discovering thousands more exoplanets, while James Webb's powerful instrumentation will allow us to analyze the atmospheres of these distant worlds for biosignatures, such as oxygen, methane, and water vapor. These missions collectively enhance our ability to determine how common Earth-like planets are and assess their potential to harbor life. While Earth-like planets once seemed rare, current evidence suggests they could be reasonably common in the galaxy. The ongoing and future missions will continue to refine these estimates and bring us closer to answering whether we are alone in the universe or part of a vast, populated cosmic landscape. Life on a tidally locked planet, where one side perpetually faces the star and the other remains in constant darkness, would present a set of unique and fascinating challenges. These planets, often found orbiting close to their parent stars, exhibit extreme environments wholly different from Earth's dynamic day-night cycle. The perpetual daylight on the star-facing side and eternal night on the opposite side would create drastic temperature contrasts, potentially ranging from scorching heat to frigid cold. Understanding how life could adapt to such conditions requires a leap in imagination, but some intriguing possibilities emerge. First, the narrow band known as the Terminator Line, the twilight zone where night meets day, offers the most likely habitat for life. In this region, the temperatures are more moderate, avoiding the extreme heat of the day side and the intense cold of the night side. Plants and photosynthetic organisms might grow in this band, utilizing the steady indirect light while possibly developing unique adaptations to cope with the low light levels. Water, if present, might also congregate here, existing as liquid due to the relatively stable conditions, thus providing a crucial resource for sustaining life. The day side, with its relentless exposure to starlight, would experience scorching temperatures. Life forms here would need extraordinary adaptations to deal with the intense heat and radiation. They might develop protective features such as thick, reflective coatings or burrow underground to avoid the surface conditions. On the night side, life forms could be adapted to near-freezing or sub-freezing temperatures, similar to extremophiles found on Earth that thrive in polar regions or deep-sea vents. For instance, organisms might rely on chemosynthesis instead of photosynthesis, extracting energy from chemical reactions in the absence of light. Human habitation on a tidally locked planet would hinge on advanced technology and keen environmental management. Settlements would most likely be built along the habitable terminator line, designed to contend with intense winds driven by the temperature disparity between the day and night sides. Sustainable energy sources, perhaps leveraging the contrast between light and dark, and efficient systems for temperature regulation and resource management would be essential. As our understanding of exoplanets grows, these speculative scenarios highlight the resilience and adaptability required for life to thrive under such extraordinary conditions. Hot Jupiters are a fascinating class of exoplanets, characterized by their large sizes comparable to Jupiter and their surprisingly close orbits around their parent stars, often completing a full orbit in just a few days. The formation and migration of these gas giants so near to their stars present intriguing questions and have driven several hypotheses aimed at unraveling this cosmic mystery. One widely accepted theory is the migration hypothesis, which suggests that hot Jupiters form much farther from their parent star, in regions of the protoplanetary disk where temperatures are low enough for ices to condense and coalesce into massive cores. These regions, akin to the location of Jupiter in our solar system, allow the accumulation of significant amounts of gas and dust, ultimately giving birth to giant planets. After their formation, these gas giants experience interactions with the surrounding disk material, leading to angular momentum exchanges that cause them to migrate inward. This process, known as disk-driven migration, can pull the planet closer to the star, upending its initially distant orbit. Another complementary model involves gravitational interactions with other nearby planets or planetary embryos. In a young, dynamically unstable planetary system, massive bodies can scatter each other into different orbits through close encounters. This mechanism, known as planet-planet scattering, can result in a giant planet being flung into a highly eccentric orbit. Over time, tidal forces exerted by the star can circularize this orbit, bringing the hot Jupiter into a stable, tight orbit very close to its star. These interactions can also involve Quasi-Lidov oscillations, where a third body induces periodic oscillations in the inclination and eccentricity of the hot Jupiter's orbit, eventually leading to inward migration. These migration processes explain the presence of hot Jupiters in stark contrast to the traditional model of planetary formation derived from our solar system. Observations of young star systems have shown evidence for both types of migration, enhancing our understanding of these mechanisms. Instruments such as the Kepler Space Telescope and upcoming missions like the James Webb Space Telescope continue to provide valuable data, revealing the diverse pathways through which planets find their places in the cosmos. The study of hot Jupiters not only enriches our knowledge of planet formation and migration, but also challenges and refines existing planetary science models. The universe is home to an array of bizarre and extreme exoplanets, each defying expectations and broadening our understanding of planetary diversity. Among the most extreme are, one of the hottest known exoplanets is Kelt 9b. Located about 670 light-years away, Kelt 9b is a gas giant that orbits its star every 1.5 days. It's exposed to such intense stellar radiation that its dayside temperatures soar to around 7,800 degrees Fahrenheit, hotter than some stars. This extreme heat causes the planet's atmosphere to evaporate, creating a tail of vaporized metals and molecules trailing behind it, much like a comet. At the other end of the temperature spectrum lies Ogle 2005 Bilgi 390 Lb. Discovered through gravitational microlensing, this planet is roughly 20,000 light-years away and orbits far from its host star. Its surface temperature hovers around -400 degrees Fahrenheit, making it a frigid, icy world. Such extreme cold suggests a surface covered in frozen hydrogen and methane, possibly hiding a subsurface ocean kept liquid by internal heat. The densest exoplanets also present remarkable extremes. For instance, Kepler-10b, located about 560 light-years away in the constellation Draco, is an ultra-dense rocky planet with a density almost twice that of Earth. Initially, it was believed to be an oversized Mercury, its extreme density hinting at a metallic composition much like the innermost planet of our solar system. Kepler-10b's dayside reaches temperatures of up to 3,600 degrees Fahrenheit, likely resulting in molten rock oceans. These are free-floating planets that don't orbit any star, drifting alone through interstellar space. Without a nearby star to provide heat, such planets can have wildly varying temperatures depending on their internal heat sources. CFB-Quazar 2149-0403, for instance, has a temperature of about 400 degrees Fahrenheit, likely heated by its own internal processes. One fascinating exoplanet is WASP-12b, an example of a hot Jupiter undergoing a process of tidal disruption. This tidally locked planet orbits so close to its star that it's being stretched into an egg shape by the star's gravity. With temperatures exceeding 4,000 degrees Fahrenheit, this extreme proximity is also causing its atmosphere to be gradually stripped away, forming a trailing stream of material being absorbed by its host star. These extreme exoplanets challenge our traditional notions of planetary formation and habitability, demonstrating the staggering variety of worlds that exist beyond our solar system. Each discovery opens new chapters in our understanding of the universe and the myriad possibilities for planets beyond our reach. In the expanse of our galaxy, binary star systems, where two stars orbit a common center, are not a rarity. Interestingly, despite the dynamic gravitational interplay between the two stars, planets can and do manage to form within these systems, often challenging our traditional models of planetary formation. In a binary star system, planets form in protoplanetary disks, which are dense concentrations of gas, dust, and other material surrounding one or both stars. The presence of two stars means that the gravitational weave is significantly more complex than in single star systems. This, however, does not inhibit the process. Rather, it introduces an added layer of cosmic ballet. As the particles in the disk collide and coalesce, they gradually build up into planetesimals and eventually protoplanets. Research involving advanced simulation techniques has shown that planets in these systems typically form in one of two primary configurations. In circumbinary systems, a planet orbits both stars in a wide, stable orbit, often beyond the reach of the star's chaotic gravitational forces. Alternatively, in circumstellar systems, a planet may orbit just one of the two stars, much closer, while the second star orbits further out. The dual star influence is a significant factor during the growth stages of these nascent planets, leading to potentially unique orbital characteristics. Recent discoveries, such as those from the Kepler Space Telescope, have confirmed the existence of several such planets, demonstrating that nature's ability to create planets is versatile enough to triumph even amidst the gravitational complexities of binary stars. Studying the atmospheres of exoplanets, those planets orbiting stars outside our solar system, opens a window into understanding not only the composition and dynamics of these distant worlds, but also the broader question of habitability and the potential for life beyond Earth. By analyzing the light that filters through or reflects off an exoplanet's atmosphere, using techniques such as spectroscopy, scientists can detect the presence of various molecules, including water vapor, methane, carbon dioxide, and even oxygen. These molecular signatures provide critical insights into the planet's atmospheric chemistry, weather patterns, and potential geological processes. Moreover, the characteristics of exoplanet atmospheres can reveal much about their origins and evolution. For instance, a predominance of hydrogen and helium might suggest a gas giant similar to Jupiter, while the presence of oxygen and water could point towards a more Earth-like world. Additionally, detecting variations in atmospheric composition over time can shed light on active phenomena such as volcanic activity or seasonal changes. Such studies can also illuminate the interactions between a planet and its host star, especially regarding how stellar radiation impacts atmospheric retention and composition. This wealth of information not only enhances our understanding of the myriad planetary systems spread across the galaxy, but also refines our models of planetary formation and sustainability, guiding our search for truly habitable worlds. Super-Earths and mini-Neptunes, Those celestial bodies with masses larger than Earth but smaller than that of Neptune present fascinating insights into planetary formation and the diversity of planetary systems. The formation of these intermediate-sized planets can generally be retraced to the early stages of a star system's birth in a protoplanetary disk, a dense, rotating disk of gas and dust enveloping a young star. In these disks, dust particles collide and stick together, eventually forming planetesimals which serve as building blocks for planets. The growth process for super-Earths, which are rocky planets with up to 10 times the mass of Earth, often involves the rapid accumulation of material before the gaseous components of the protoplanetary disk dissipate. The core accretion model suggests that these planets form by the gradual buildup of a solid core, which can gather gas from the disk if it's sufficiently massive. However, they typically aren't large enough to morph into gas giants. Conversely, mini-Neptunes, which are defined by their extended atmospheres of hydrogen and helium over a solid core, likely follow a similar growth trajectory, but manage to capture a more substantial gaseous envelope. These planets may form further out in the cooler regions of the disk, where gas accretion is more efficient, or they might migrate inward after their formation. Recent observational missions, such as those carried out by the Kepler Space Telescope, have identified that these categories of planets are among the most common types in our galaxy. The fact that they do not appear in our own solar system adds a compelling layer to the study of planetary systems, suggesting a vast and varied landscape of planet formation mechanisms. Understanding these processes enhances our grasp of planet formation theories, offering clues on the initial conditions and subsequent evolutionary pathways that can lead to the myriad planetary configurations observed in the universe. The quest for identifying an Earth 2.0, a true twin to our home planet, fascinates astronomers and captures the imagination of the public. Scientists are focusing on locating Earth-sized or slightly larger exoplanets in the habitable zones of their stars, where conditions might be right for liquid water to exist. The habitable zone, often referred to as the Goldilocks zone, represents the region around a star where temperatures are just right, not too hot and not too cold, for maintaining liquid water, a key ingredient for life as we know it. Advancements in telescope technology, such as those seen with the Kepler Space Telescope and its successor, the Transiting Exoplanet Survey Satellite, TESS, have exponentially increased the number of known exoplanets. These sophisticated instruments can detect the minute dimming of a star's light as a planet crosses in front of it, known as a transit. Through these discoveries, we've identified several promising candidates that tick many of the boxes for Earth-like features, such as Kepler 186f and Proxima Centauri b, both situated within their respective habitable zones. The next frontier involves the detailed study of these candidate planets, particularly their atmospheres, to determine their true potential for habitability. The James Webb Space Telescope and future missions like the European Space Agency's Ariel spacecraft will allow us to scrutinize atmospheric compositions with unprecedented precision. Detecting gas compositions and potential biosignatures, like oxygen, methane, and other organic molecules, will be crucial in assessing whether these worlds harbor environments conducive to life. While we haven't found an exact Earth analog yet, the accelerating pace of discoveries and technological advancements suggests that finding Earth 2.0 is no longer a mere fantasy, but an exciting, attainable goal within the near future. Rogue planets, also known as interstellar or free-floating planets, are fascinating celestial objects that wander the galaxy without orbiting any star. Their formation and evolution tell an intriguing story of cosmic dynamics and the volatility of young planetary systems. These planets could originate in several ways. One leading hypothesis is that rogue planets form within the protoplanetary disks surrounding young stars, just as regular planets do. However, turbulent interactions and gravitational influences from neighboring planets or passing stars can eject these nascent worlds from their original orbits, sending them drifting into the interstellar void. Another potential formation pathway suggests that rogue planets might coalesce directly from the collapse of gas and dust clouds, following a process similar to star formation but lacking sufficient mass to ignite nuclear fusion. This direct collapse model implies that rogue planets might share more characteristics with brown dwarfs, which are substellar objects that also form from collapsing gas clouds but never reach the critical mass required to sustain fusion reactions in their cores. Once adrift, rogue planets evolve in isolation, unfree from the radiation and tidal forces of a host star. This independence means their surfaces can be exceedingly cold, potentially harboring frozen atmospheres or oceans if they have any liquid elements. However, internal heating sources, such as radioactive decay or residual heat from their formation, could sustain subsurface oceans beneath icy shells, raising intriguing possibilities about their capacity to harbor life in isolated ecosystems. As our detection technologies improve, including gravitational microlensing techniques and sensitive infrared surveys, we've started to identify more of these elusive wanderers, offering valuable insights into the chaotic processes that shape planetary systems and the potential hidden reservoirs of life in the universe. Standing on the surface of a super-Earth, a planet larger and more massive than Earth but still rocky in nature, would be an extraordinary experience, distinctly different from anything we know. Imagine a world where gravity is appreciably stronger than Earth's, given its greater mass. This increased gravity means that every movement, every step, and every heartbeat requires more effort. Depending on the exact mass and radius of the super-Earth, the gravitational force could be anywhere from slightly stronger to several times greater than what we experience on Earth. This would make you feel significantly heavier, reducing your ability to jump or move quickly and influencing how you structure habitats and conduct daily activities. The atmosphere of a super-Earth might also present unique characteristics. A planet with a more massive core could have retained a thicker atmosphere, possibly rich in gases like hydrogen and helium, affecting air pressure and climate. If the super-Earth has a robust magnetic field, it might shield the surface from harmful cosmic radiation, creating potentially habitable conditions. The thicker atmosphere could lead to more intense weather patterns. Imagine powerful storms and possibly denser cloud formations that affect light and heat distribution. If the planet is within the habitable zone of its star, liquid water might exist, altering the landscape with vast oceans, rivers, and perhaps lush vegetation unlike anything seen on Earth. The geology of a super-Earth would also be fascinating. The increased gravity might result in shorter and stubbier mountain ranges compared to those on Earth, as the weight of rock layers is greater and hence they can't rise as high without collapsing. The surface would likely be marked with diverse terrain, which might include vast plains, deep canyons, and expansive plateaus shaped by the planet's intense internal heat and tectonic activity. Overall, standing on a super-Earth would provide a constant reminder of its powerful gravitational pull and might offer sights and experiences that redefine our understanding of planetary life. Dark energy is one of the most enigmatic and captivating concepts in modern cosmology. This mysterious force constitutes about 70% of the universe's total energy content and is believed to be the driving force behind the accelerated expansion of the universe. Unlike dark matter, which exerts gravitational pull, dark energy acts in opposition to gravity, pushing regions of space apart. Its exact nature remains one of the greatest scientific mysteries, but it is often associated with the cosmological constant, a term first introduced by Albert Einstein in his equations of general relativity and later revived to explain observations of the expanding universe. The discovery of dark energy stems from the late 1990s, when astronomers observed distant supernova and realized that these stellar explosions were dimmer and therefore further away than expected. This unexpected acceleration suggests that instead of slowing down due to gravitational attraction, the universe's expansion rate is accelerating, indicating the presence of a repulsive force. Dark energy affects the large-scale structure of the cosmos, influencing galaxy formation, clusters, and the ultimate fate of the universe. If the influence of dark energy continues to dominate, it could lead to a future scenario known as the Big Freeze, where galaxies drift so far apart that stars deplete their nuclear fuel without forming new stars, eventually leaving a cold, dark, and sparse cosmos. Various theoretical models attempt to describe dark energy, including quintessence, which proposes a dynamic field that changes over time, and modifications of gravity on large scales. Upcoming observations, especially from missions like the Euclid Space Telescope and the Wide Field Infrared Survey Telescope, WF-FIRST, aim to map the distribution of galaxies and test predictions about cosmic acceleration, hopefully bringing us closer to understanding this profound aspect of our universe. These studies not only elucidate the nature of dark energy, but also transform our comprehension of fundamental physics and the ultimate destiny of all cosmic structures. Galaxy clusters are the most massive gravitationally bound structures in the universe, consisting of hundreds to thousands of galaxies, vast amounts of hot gas, and dark matter all held together by gravity. The formation and evolution of these colossal structures provide valuable insights into the large-scale properties of the universe. The story of galaxy clusters begins in the early universe, where initial density fluctuations in the cosmic microwave background, a relic radiation from the Big Bang, seeded regions of higher matter concentration. As the universe expanded and cooled, these density fluctuations grew under the influence of gravity, pulling in surrounding dark matter and gas. Dark matter, being the dominant mass component of the universe, plays a critical role as the scaffolding upon which galaxy clusters form. Over billions of years, smaller structures merged through a process called hierarchical clustering. This means that smaller galaxy groups and protoclusters combine to form larger and more massive clusters, gradually building up to the enormous structures we observe today. Throughout this process, galaxies interacted and sometimes merged, altering their shapes and triggering star formation. The evolution of galaxy clusters is marked by dynamic processes. The intracluster medium, comprising hot X-ray emitting gas that can reach temperatures of up to 100 million degrees Kelvin, is a key feature of these clusters. This hot gas results from the kinetic energy of gas particles being transformed into thermal energy as they collapse into the cluster's gravitational potential well. Galaxy clusters also experience interactions and collisions that can lead to phenomena such as gravitational lensing, where the cluster's mass bends light from background galaxies, providing a cosmic magnifying glass effect. Studying these interactions not only helps in mapping the distribution of dark matter, but also in understanding the rate of cluster evolution. Advanced telescopes and surveys, such as those conducted by the Hubble Space Telescope, the Chandra X-ray Observatory, and upcoming instruments like the James Webb Space Telescope, continue to enhance our understanding of galaxy clusters. These observations refine our models of cosmological structure formation and evolution, offering clues about the nature of dark matter and dark energy, thus unraveling deeper mysteries of the cosmos. The filamentary structure of the cosmic web, the vast network of interconnected galaxies, galaxy clusters, and dark matter that stretches across the universe, is a direct result of the gravitational influence exerted by dark matter and the dynamics of cosmic expansion. This intricate cosmic architecture is shaped by the primordial density fluctuations in the early universe, which were initially imprinted on the cosmic microwave background radiation shortly after the Big Bang. In the early stages of the universe, tiny variations in the density of matter led to the formation of regions of higher and lower mass concentrations. Dark matter, which makes up about 85% of the universe's total matter content, began to clump together in response to these density fluctuations. Over time, gravity amplified these perturbations, causing the denser regions to attract more matter and grow even denser. This process created a web-like pattern of high-density regions, connected by elongated filaments of dark matter and ordinary matter, with vast voids in between. As gravity continued to pull matter into these filaments, gas and dust followed the dark matter's lead, resulting in the formation of galaxies and galaxy clusters along these vast strands. The intersections of filaments, known as nodes, became hotbeds for galaxy and cluster formation, where multiple filaments converge, creating regions of extraordinarily high density. These nodes are essentially the cosmic hubs of the universe, connected by the filamentary roads of the cosmic web. Modern astronomical observations and simulations, such as those using the Sloan Digital Sky Survey and the Millennium Simulation, have provided detailed maps of the cosmic web, confirming its filamentary structure and enhancing our understanding of large-scale cosmic evolution. These studies show that the cosmic web's texture is crucial for the formation of galaxies and other cosmic structures, profoundly influencing the dynamics and distribution of matter in the universe. As our observational tools and computational models continue to improve, we will gain even deeper insights into the mechanisms driving this grand cosmic tapestry. Cosmic voids, the vast empty regions between the filamentary structures of the cosmic web, represent some of the most fascinating expanses in the universe. These voids, which can span tens to hundreds of millions of light-years across, form as a natural consequence of the gravitational evolution of matter after the Big Bang. In the early universe, slight density fluctuations resulted in regions of higher and lower matter density. Over billions of years, the gravitational force amplified these initial differences. High-density regions attracted more mass, leading to the formation of galaxies and clusters, while low-density regions were left relatively vacant, evolving into cosmic voids. The process of void formation involves matter being pulled away from these underdense regions toward the denser filaments and clusters. Essentially, the rich get richer and the poor get poorer. These voids are not completely empty, but contain significantly fewer galaxies and less matter compared to the denser parts of the universe. The sparse galaxies within cosmic voids are often isolated and tend to be small, dim, and irregularly shaped, unlike their more abundant counterparts in the dense clusters. Additionally, these voids have lower gas content, and any remaining gas is usually at a much lower temperature compared to the hot, X-ray emitting gas found in galaxy clusters. Interestingly, cosmic voids serve as excellent laboratories for studying various cosmological phenomena. Because they are relatively simple environments with less gravitational complexity, they offer a unique setting for examining dark energy's effects on cosmic expansion. The dynamics of how galaxies move within and around voids also provide valuable insights into the large-scale structure and evolution of the universe. Advanced surveys and simulations, such as those conducted by the Dark Energy Survey and the Illustris simulation, have been instrumental in mapping these voids and understanding their role in the cosmos. As research progresses, cosmic voids will continue to reveal intriguing aspects of how the universe and the mysterious forces driving its evolution operates. The largest structures in the universe are awe-inspiring in their scale and complexity, stretching across hundreds of millions of light-years and composed of countless galaxies, dark matter, and intergalactic gas. These colossal formations include galaxy clusters, superclusters, filaments of the cosmic web, and vast cosmic voids, each contributing to the grand architecture of the cosmos. Among these, the most enormous structures are galaxy superclusters, which are collections of galaxy clusters bound together by gravity to create immense conglomerates. One of the most well-known superclusters is the Laniakea supercluster, which extends over 500 million light-years and contains around 100,000 galaxies, including our own Milky Way. Another colossal structure is the Hercules Corona Borealis Great Wall, which is currently considered the largest known structure in the observable universe. This immense wall of galaxies spans over 10 billion light-years, challenging our understanding of cosmic scale and structure. These superclusters, strung together by vast filaments of dark matter and intergalactic gas, form the nodes and connections of the cosmic web. Filaments themselves are enormous, often stretching over several hundred million light-years, and act as the spine of the cosmic skeleton, guiding the formation and distribution of galaxies. The cosmic web's interconnecting structure is punctuated by enormous voids, vast empty spaces that make up large portions of the universe. These large-scale structures provide crucial insights into the universe's formation and evolution. They help astronomers understand the distribution of dark matter and the influence of dark energy in driving the universe's accelerated expansion. Ongoing and future surveys utilizing advanced telescopes and computational simulations continue to map these vast structures in higher detail, revealing the intricacies of the universe on its grandest scales. The study of these structures not only broadens our knowledge of cosmological principles, but also uncovers the fundamental forces shaping our universe's ultimate destiny. Galactic superclusters, the largest coherent structures in the universe, influence each other primarily through the force of gravity and the large-scale dynamics of cosmic expansion. These colossal assemblies, consisting of multiple galaxy clusters and hundreds of thousands of individual galaxies, are interconnected by filaments of the cosmic web, creating a complex network. While superclusters themselves can be hundreds of millions of light-years apart, their gravitational fields extend far beyond their visible boundaries, subtly pulling on neighboring structures and influencing their motions. The interaction between superclusters happens over incredibly long timescales, often spanning billions of years. The gravitational pull they exert on each other can lead to large-scale flows of galaxies and dark matter, often converging towards the densest regions. This movement is sometimes referred to as peculiar velocity, which is the velocity relative to the overall expansion of the universe. These flows can lead to phenomena like the Great Attractor, a mysterious region of space towards which our Milky Way and thousands of other galaxies are moving, influenced by the gravitational pull of several neighboring superclusters. Additionally, as superclusters move and evolve, they can influence the structure of the cosmic web. The dense regions at the intersections of filaments, where superclusters reside, can become even denser due to gravitational accretion from surrounding voids and filaments. High-energy interactions, such as galaxy mergers and collisions of galaxy clusters within superclusters, also play a role in redistributing mass and energy. These events can trigger star formation, modify galaxy morphology, and generate enormous amounts of hot gas and X-ray emissions, enriching the intergalactic medium with heavy elements. Recent observations and simulations, such as those from the Sloan Digital Sky Survey and the Illustris TNG project, are beginning to unveil the complexities of these interactions. These studies help us understand how large-scale cosmic structures grow and evolve, and how their intricate dance shapes the universe's overall architecture. By mapping the motions and distributions of superclusters and their constituent galaxies, astronomers are piecing together the grand narrative of cosmic evolution, offering deeper insights into the underlying forces governing the universe. The Great Attractor is a gravitational anomaly located in the Laniakea supercluster, a mammoth conglomeration of galaxies, including our own Milky Way. Discovered in the late 20th century, the Great Attractor is intriguing because it exerts a significant gravitational pull on our galaxy and many others, causing them to move towards it at speeds exceeding 600 kilometers per second. This peculiar motion is in addition to the general expansion of the universe, indicating that a substantial mass concentration lies in this region. The exact nature of the Great Attractor is somewhat obscured because it's located in the so-called zone of avoidance, an area of the sky heavily obscured by the Milky Way's plane. However, extensive observations in various wavelengths, including X-rays and radio waves, have helped researchers peer through the galactic dust and identify what lies in this mysterious region. It's now thought that the Great Attractor is a complex assembly of several galaxy clusters, with one of the most prominent being the Norma cluster, also known as Abell 3627. Further, the Great Attractor is part of an even larger structure called the Shapley supercluster, which contains many clusters and superclusters and represents one of the densest and most massive regions in the nearby universe. The mass concentration in this area is so enormous that it not only pulls our local group of galaxies, but also affects the motion of other neighboring superclusters. The study of the Great Attractor enriches our understanding of the large-scale structure of the universe and the forces that shape it. It also underscores the complexity of gravitational interactions over vast distances, shedding light on the underlying distribution of both visible and dark matter. With advancing technology and ongoing surveys, astronomers continue to uncover the hidden details of this compelling cosmic enigma, contributing to a more complete picture of the universe's grand tapestry. Dark matter halos play a pivotal role in the formation and evolution of galaxies, acting as the unseen scaffolding upon which galaxies are built. Comprising about 85% of the total matter in the universe, dark matter exerts gravitational forces that are essential for collecting and concentrating the ordinary baryonic matter, such as gas and dust, needed to form stars and galaxies. Without dark matter halos, the universe's baryonic matter would be too diffuse to coalesce into the dense structures required to forge galaxies. The process begins in the early universe, shortly after the Big Bang, when small fluctuations in the density of dark matter seeds gravitational wells. Over time, these small clumps of dark matter attract more and more mass, growing into larger halos. This accumulation continues, with dark matter halos merging and accreting additional mass, establishing the large-scale structure of the cosmos. As these halos evolve, they create deep gravitational wells that drag in ordinary matter. Once baryonic matter falls into these dark matter halos, it begins to cool and contract, eventually leading to the formation of rotating disks of gas that become the birthplaces for stars and galaxies. The intricate dance between dark matter and baryonic matter governs various stages of galaxy formation, from the initial gathering of gas to the intricate processes that regulate star formation rates. For instance, gas cooling mechanisms and feedback processes from supernovae and active galactic nuclei, AGN, can further modulate galactic growth, but the primary gravitational framework is provided by the encompassing dark matter halo. The influence of dark matter halos extends beyond initial galaxy formation. They also impact the dynamics and structure of galaxies. For example, the rotation curves of spiral galaxies, plots of rotational velocities against radial distance from the galaxy center, remain flat at larger distances rather than dropping off as expected from visible matter alone. This flat rotation curve can be explained by the presence of an extensive dark matter halo enveloping the galaxy, providing the necessary additional gravitational pull. Advanced simulations, such as those run by the Illustris and Eagle projects, and observational data from telescopes like the Hubble Space Telescope and the upcoming James Webb Space Telescope, continue to reveal the profound impact of dark matter halos on the cosmic architecture. These studies not only deepen our understanding of galaxy formation and evolution, but also provide essential insights into the nature of dark matter itself, one of the most fundamental mysteries in modern astrophysics. Cosmic inflation is a theory that proposes a brief but extremely rapid expansion of the universe immediately following the Big Bang, from roughly 10 circumflex 36 to 10 circumflex 32 seconds after the initial cosmic creation. This exponential expansion increased the universe's size by a factor of at least 10 circumflex 26, smoothing out any initial irregularities and setting up the large-scale structure we observe today. The idea of inflation was first introduced by physicist Alan Guth in the early 1980s to resolve several puzzling issues in cosmology, such as the horizon problem, the flatness problem, and the absence of magnetic monopolies. The driving force behind cosmic inflation is thought to be a hypothesized field called the inflaton field, which possessed a high-energy potential. During inflation, the inflaton field was initially in a metastable high-energy state. As it decayed from this state, it released vast amounts of energy, causing space-time to expand at an extraordinarily accelerated rate. This expansion was so rapid that it stretched any microscopic quantum fluctuations in the inflaton field to macroscopic scales, which later became the seeds for large-scale structures like galaxies and clusters of galaxies. These stretched quantum fluctuations are now observed as the anisotropies in the cosmic microwave background, CMB, the leftover radiation from the Big Bang. The end of inflation, sometimes referred to as reheating, transitions the universe into the hot, dense state we associate with the Big Bang. As the inflaton field settled into its minimum energy state, it decayed into particles and radiation, leading to the conditions necessary for nucleosynthesis, the formation of atomic nuclei, and eventually the formation of stars and galaxies. The rapid inflation also ensured that the observable universe appears remarkably uniform and isotropic, solving the horizon problem by allowing different regions of space to be in causal contact before inflation stretched them apart. The evidence for cosmic inflation primarily comes from observations of the CMB, particularly the detailed measurements of temperature fluctuations by missions like the Cosmic Background Explorer, Wilkinson Microwave Anisotropy Probe, and Planck satellites. These observations reveal a nearly uniform but slightly perturbed early universe, consistent with the predictions of inflation. Further research and upcoming observations aim to detect primordial gravitational waves, another potential signature of inflation, which would provide even more robust evidence for this transformative epoch in cosmic history. Thus, cosmic inflation not only shaped the early universe in a profound way, but also laid the groundwork for the intricate cosmic structure we see today. Detecting and mapping dark matter in the universe is a fascinating challenge that has intrigued scientists for decades. One primary method we use to unveil this elusive substance is through observing its gravitational effects on visible matter, particularly galaxies and clusters of galaxies. When we look at the rotation curves of galaxies, we notice that the stars at the outskirts move much faster than they should based on the visible mass alone. This discrepancy suggests an unseen mass, constituting about 85% of the total mass of the universe. Astronomers use these rotational speeds to infer the presence and distribution of dark matter. Another powerful technique involves gravitational lensing, where the presence of dark matter is detected by observing how it bends light from distant stars and galaxies. This bending, predicted by Einstein's theory of general relativity, acts as a sort of cosmic magnifying glass. By analyzing the extent to which the light is warped, scientists can construct detailed maps of dark matter's distribution in the universe. These maps have confirmed that dark matter forms vast web-like structures that act as the backbone for galaxy formation. These cosmic webs wouldn't be as visible if not for the small distortions they cause in the light from the furthest reaches of the cosmos, providing an indirect yet profound glimpse into this unseen component of the universe. Magnetars, a type of neutron star, produce incredibly strong magnetic fields, often more than 1,000 times stronger than those of typical neutron stars, through mechanisms rooted in the tumultuous events during and after their formation. When a massive star exhausts its nuclear fuel, it undergoes a supernova explosion, collapsing its core into a dense neutron star packed with protons and neutrons. In some cases, this rapid collapse, combined with the conservation of angular momentum, can amplify the magnetic field exponentially. Initially, the star's magnetic field might not be extraordinary, but as the star's core collapses into a space just about 12 miles in diameter, the field lines are immensely concentrated. Additionally, certain theories suggest that magnetars may owe their intense magnetic fields to processes known as dynamo action, which could occur within the nascent neutron star. During the first few seconds to minutes after the birth of a neutron star, the extremely fluid and highly conductive interior can undergo differential rotation, where the core rotates at a different speed than the outer layers. This differential rotation might generate potent electric currents, further intensifying the magnetic field to levels exceeding 1 quadrillion Gauss, roughly 1 trillion times stronger than Earth's magnetic field. Following these dramatic initial moments, the magnetic field stabilizes but remains profoundly powerful, occasionally resulting in seismic activity on the magnetar's crust, unleashing bursts of X-rays and gamma rays that outshine entire galaxies for brief moments, providing a dramatic celestial spectacle. Fast radio bursts, or FRBs, are among the most enigmatic phenomena in astrophysics, characterized by sudden intense bursts of radio waves lasting mere milliseconds. The exact origins of FRBs are still shrouded in mystery, but several compelling theories exist. One leading hypothesis suggests that these bursts are generated by highly magnetized and rapidly rotating neutron stars, specifically magnetars. During the active phases, magnetars can release colossal amounts of energy through starquakes or magnetic reconnection events. These violent episodes can produce intense radio emissions, which we observe as FRBs. Another intriguing possibility is that FRBs might stem from catastrophic cosmic events, such as the collision of neutron stars or the collapse of a massive star into a black hole. These cataclysms release tremendous amounts of energy, capable of producing the powerful radio bursts that illuminate our instruments here on Earth. Additionally, some theories propose more exotic origins, like interactions between pulsars and their surrounding environments, or even hypothetical extraterrestrial technologies. Regardless of their source, each FRB detected offers valuable data that inch us closer to unraveling this cosmic mystery, showcasing not only the extreme conditions of our universe, but also the ingenuity of human curiosity and exploration. The survival of a star through a supernova explosion is a testament to the complex dynamics that govern stellar evolution. Not all stars are entirely obliterated in these cataclysmic events. Some manage to leave behind a core remnant. A common outcome is the formation of a neutron star or a black hole, depending on the initial mass of the progenitor star. For lower mass stars, what's left behind is often a neutron star, a dense, city-sized object composed primarily of neutrons. This remnant forms when the core collapses under gravity, packing its matter densely enough to withstand further collapse due to neutron degeneracy pressure. In other cases, particularly for stars that start with an exceptionally high mass, the core collapse doesn't stop at the neutron star stage but continues until a black hole forms. This happens because the remnant's gravitational pull is so intense that not even light can escape once past the event horizon. Interestingly, there's also a scenario where binary star systems are involved. If one star in a binary system undergoes a supernova, it might impulsively kick off its companion star. The surviving companion star can remain in orbit around the resultant neutron star or black hole, or be flung into space as a runaway star. This interplay reveals much about the resilience and the transformative power of these stellar explosions, showcasing how some remnants manage to endure, becoming fascinating objects for further cosmic study. The pulsations of variable stars such as Cepheids and RR Lyrae stars are driven by complex processes occurring within their interiors, primarily governed by the balance of pressure and gravity. One of the most studied mechanisms behind these pulsations is the Kappa mechanism. In this process, a star's outer layers become partially ionized. As the star compresses, the opacity of these partially ionized layers increases, trapping heat and causing the star's outer layers to expand. Conversely, as the star expands, the opacity decreases, allowing the heat to escape, leading to a cooling and contraction of the outer layers. This cyclic process of compression and expansion creates the rhythmic pulsations observed in these stars. Additionally, these pulsations can be influenced by changes in the star's temperature and internal structure. For example, Cepheid variables undergo a deep layer heating effect, where ionization of helium plays a critical role. When helium is singly ionized, it absorbs energy and causes the outer layers to swell. Once these layers have expanded and cooled, helium recombines, releasing energy that then drives the layers to contract once more. This periodic heating and cooling maintain the pulsations. These stellar oscillations are not just astrophysical curiosities, they are vital tools for measuring cosmic distances. By examining the period and luminosity of these pulsating stars, astronomers can accurately determine their distance from Earth, leading to a better understanding of the scale of the universe and the structure of our Milky Way galaxy. Binary stars exchange mass through a fascinating and dynamic process largely governed by their gravitational interaction and the evolution of the stars involved. One common way this exchange occurs is through Roche lobe overflow, a scenario where one star in a binary system expands to fill its Roche lobe, the region around a star within which orbiting material is gravitationally bound to that star. As the star enlarges, often during its red giant phase, it can spill material over its Roche lobe boundary onto its companion star, leading to significant transfer of mass. This process can profoundly affect the evolution of both stars, often rejuvenating the recipient star and stripping the donor star down to its core. In certain cases, another mechanism called stellar wind accretion comes into play. Here, mass transfer occurs through winds emanating from the surface of the more evolved star. These winds can be captured by the gravitational field of the companion star, particularly if the two stars are relatively close. The accreting star can capture a portion of this wind, leading to a more gradual and often less dramatic mass exchange compared to Roche lobe overflow. These interactions are critical in shaping the evolutionary paths of binary stars, sometimes leading to phenomena like X-ray binaries, where a compact object such as a neutron star or black hole accretes matter from a companion, emitting powerful X-rays as a result. Blue stragglers are an intriguing phenomenon in stellar astrophysics, appearing as anomalously young and hot stars within aged stellar populations, such as globular clusters. These stars defy the standard stellar evolution models, which predict that stars of similar mass should age and evolve at comparable rates. Several theories attempt to explain their formation, with the two primary mechanisms being stellar collisions and mass transfer in binary systems. In the dense environments of globular clusters, stars are packed closely together, increasing the likelihood of direct collisions or mergers. When two stars collide, they can amalgamate to form a single, more massive star. This merger results in a rejuvenated star that burns hotter and appears bluer than other stars of similar age, leading to the appearance of a blue straggler. The reconstituted star seemingly resets its evolutionary clock, making it appear younger and more luminous despite actually being as old as the rest of the stars in the cluster. Mass transfer in binary systems offers another compelling explanation. In this scenario, a star in a close binary system can overflow its Roche lobe, transferring mass to its companion. The recipient star gains significant mass and is thereby reinvigorated, increasing its temperature and brightness. This mass acquisition slows its evolutionary progression, effectively giving it a new lease on life as a blue straggler. The combination of these processes, collisional rejuvenation and binary mass transfer, provides a robust framework for understanding how blue stragglers defy the conventional wisdom of stellar aging, allowing them to stand out as enigmatic outliers in the stellar population. Brown dwarfs are fascinating celestial objects that straddle the line between the largest planets and the smallest stars. Their formation process shares similarities with that of stars, starting in the dense regions of molecular clouds. These clouds of gas and dust can collapse under their own gravity, fragmenting into smaller clumps. As these clumps contract, their cores heat up. However, unlike stars, brown dwarfs do not accumulate enough mass to ignite sustained hydrogen fusion in their cores due to the lack of critical mass, usually less than about 75 times that of Jupiter. After forming, brown dwarfs undergo a phase of gradual cooling and contraction. Initially, they might briefly ignite deuterium fusion, but this process is short-lived and insufficient to sustain a long-term energy output. Over time, brown dwarfs emit light primarily in the infrared spectrum and gradually cool and fade. Their atmospheres often display complex weather patterns, similar to those seen on gas giant planets with cloud bands and storms. Despite their lack of sustained nuclear fusion, brown dwarfs can help bridge the understanding between planetary and stellar formation processes, offering a unique perspective on the diversity of celestial bodies in our universe. Gamma-ray bursts, GRBs, are among the most explosive events in the universe, often triggered by the cataclysmic death of massive stars. One of the primary mechanisms thought to generate these extraordinary bursts of gamma rays is the collapse of a massive star's core, leading to a type of supernova known as a hypernova. When a star much larger than our Sun exhausts its nuclear fuel, its core can no longer support the outer layers, resulting in a catastrophic collapse. This core collapse can create a rapidly rotating black hole or a highly magnetized neutron star known as a magnetar. The intense gravitational forces and rapid rotation drive material into highly energetic jets, which drill through the outer layers of the star. As these jets break free, they accelerate particles to near-light speeds, causing collisions that produce copious amounts of gamma rays. If one of these jets is oriented toward Earth, we observe it as a gamma-ray burst. This process not only results in a brief flash of gamma rays, sometimes lasting from milliseconds to several minutes, but it also produces an afterglow observable across various wavelengths, such as X-rays, optical and radio waves, as the jet interacts with the surrounding interstellar medium. Another source of gamma-ray bursts is the merger of compact stellar remnants in binary systems, such as two neutron stars colliding, or a neutron star merging with a black hole. These violent mergers also produce intense jets of relativistic particles and gamma rays, albeit through a somewhat different mechanism involving the complex interplay of extreme gravitational and magnetic forces. Whether through the death throes of massive stars or the collision of compact objects, gamma-ray bursts exemplify the universe's ability to produce astounding feats of energy with profound implications for our understanding of cosmic phenomena. Neutron stars produce pulsars through a combination of their rapid rotation and intense magnetic fields. When a massive star undergoes a supernova explosion and its core collapses, it forms a neutron star, which is incredibly dense, often packing more mass than our Sun into a sphere just about 12 miles in diameter. This collapse leads to the conservation of angular momentum, causing the neutron star to spin at incredibly high speeds, sometimes hundreds of times per second. Additionally, the collapsing core amplifies the magnetic field to extreme strengths, up to 1 trillion times stronger than Earth's magnetic field. The magnetic field channels charged particles along the magnetic poles of the neutron star, accelerating them to relativistic speeds. These high-energy particles emit beams of electromagnetic radiation, including radio waves, X-rays, and gamma rays, along the magnetic axis. However, these magnetic poles are typically not aligned with the star's rotational axis. As the neutron star spins, the radiation beams sweep across the sky like cosmic lighthouses. If one of these beams points towards Earth, we detect a pulse of radiation each time it crosses our line of sight, creating the periodic signals we observe as pulsars. These pulses can be incredibly regular, with some pulsars serving as highly precise cosmic clocks. The precise timing makes pulsars valuable tools for various astrophysical applications, including testing the limits of general relativity, probing the interstellar medium, and even indirectly detecting gravitational waves. Pulsars thus offer a unique and fascinating glimpse into the extreme conditions at the end of a massive star's life cycle, showcasing the universe's clockwork precision amidst its awe-inspiring violence. Hypergiants are among the most luminous and massive stars in the universe, exhibiting extreme brightness due to several intrinsic characteristics tied to their enormous sizes, high temperatures, and significant rates of fusion. These stars typically possess masses ranging from tens to over 100 times that of our Sun, which triggers incredibly intense nuclear fusion reactions in their cores. The immense gravitational pressure in the core of such a massive star facilitates these reactions, producing vast amounts of energy that radiate outward and maintain the star's structural stability. Moreover, hypergiants are often exceedingly hot, with surface temperatures that can range from several thousand to tens of thousands of degrees Kelvin. This high temperature means that they emit copious amounts of light, especially in the ultraviolet spectrum, contributing further to their extreme brightness. Additionally, hypergiants have enormous radii, which magnify their luminous output. The Stefan Boltzmann law, which states that a star's luminosity is proportional to its surface area and the fourth power of its surface temperature, mathematically explains why these giant stars radiate so much energy. Beyond their intrinsic properties, hypergiants often undergo significant mass loss through powerful stellar winds driven by radiation pressure. These winds manifest as massive outflows of gas and can form extended luminous shells around the star, sometimes further increasing their apparent brightness. Complex interactions between the star's radiation and the ejected material, such as shocks and recombination, can also enhance their luminosity. These processes collectively create a spectacle of light, making hypergiants some of the most magnificent and brilliant objects in the night sky, despite their relatively short lifespans on the cosmic scale. The formation of supermassive black holes, SMBHs, in galactic centers is a subject of intense astrophysical research, intertwining multiple processes over vast cosmic timescales. One leading theory suggests that these colossal objects, often harboring masses ranging from millions to billions of times that of our Sun, originate from the direct collapse of massive gas clouds in the early universe. These gas clouds, if massive and dense enough, could bypass the typical star formation process and collapse directly into a black hole, providing a seed for further growth. Another pathway involves the merging of intermediate mass black holes or the remnants of massive stars. In dense star clusters found in the earlier universe, frequent interactions and mergers could lead to the formation of larger black holes. These intermediate mass black holes would then migrate towards the center of their galaxy due to dynamical friction and eventually coalesce, growing into a supermassive entity. Over time, these nascent SMBHs would gain mass by accreting gas, dust, and other objects from their surroundings. During active galactic nuclei (AGN) phases, where the SMBH accretes material at a high rate, they emit vast quantities of energy, often observed as quasars, further enhancing their growth. Gravitational interactions during galaxy mergers also play a crucial role. When galaxies merge, their central black holes can spiral inwards and eventually merge, forming a more massive supermassive black hole. This process of hierarchical merging could explain the presence of extremely massive black holes in the centers of giant galaxies today. Such mergers would not only combine the mass of the black holes, but also trigger the accretion of additional surrounding gas and stars, leading to further growth. Understanding SMBHs is crucial for comprehending the history and evolution of galaxies, as their presence influences star formation, galactic dynamics, and the distribution of matter across the cosmos. These enigmatic and powerful objects remain a focus of astronomical fascination, revealing the intricate dance of gravity and matter over billions of years. The fate of information that falls into a black hole is one of the most profound puzzles in modern theoretical physics, often referred to as the black hole information paradox. According to classical general relativity, any matter or information that crosses the event horizon, the boundary beyond which nothing can escape, becomes irretrievably trapped. The details of the fallen matter, such as its composition and quantum states, are thought to be lost to the outside universe, with only mass, electric charge, and angular momentum of the black hole being observable. This idea aligns with the so-called no-hair theorem. However, this classical view clashes with the principles of quantum mechanics, which stipulate that information must be conserved and not destroyed. This conflict has spurred extensive theoretical work to reconcile these two foundational pillars of physics. One prominent line of thought arose with Stephen Hawking's discovery that black holes can emit radiation, now known as Hawking radiation, due to quantum effects near the event horizon. While this radiation causes black holes to slowly lose mass and eventually evaporate, it presents a conundrum. If the black hole evaporates entirely, does the information that fell into it disappear as well? Various proposed solutions aim to resolve this paradox. One idea is that information might be encoded in the Hawking radiation itself, although how this could happen without violating other quantum principles remains unclear. Another hypothesis involves the concept of black hole complementarity, suggesting that information is both reflected at the event horizon and passes through, without any observer being able to witness a violation of information preservation. A more recent and speculative approach is the firewall hypothesis, suggesting that a highly energetic barrier at the event horizon destroys incoming information, although this idea also challenges established physics principles. The information paradox remains unresolved, a tantalizing intersection where the laws of quantum mechanics and general relativity meet. Solving it may require a new, unified theory of quantum gravity, offering deeper insights into the very fabric of reality. Binary black hole systems evolve and eventually merge through an intricate dance dictated by the interplay of gravitational forces and relativistic effects. Initially, two black holes can form a binary system through various scenarios, such as the collapse of massive stars in a binary system, or through dynamic interactions within dense star clusters, where individual black holes can gravitationally capture one another. Once a binary black hole system is established, its evolution is driven primarily by the emission of gravitational waves, as predicted by Einstein's theory of general relativity. As the two black holes orbit each other, they generate ripples in the fabric of spacetime known as gravitational waves. These waves carry away energy and angular momentum from the system, causing the black holes to spiral closer together over time. The rate of energy and momentum loss increases as the black holes draw nearer, leading to a faster orbital decay and tighter spirals. This process can persist for millions to billions of years, depending on the initial separation and masses of the black holes. When the black holes get sufficiently close, typically within a few hundred kilometers, the emission of gravitational waves becomes extraordinarily intense. This final phase of inspiral culminates in the merger, where the two black holes collide and coalesce into a single, more massive black hole. The merger releases a significant burst of gravitational waves, detectable by instruments such as the Laser Interferometer Gravitational Wave Observatory, LIGO, and Virgo. These detections have opened a new observational window into the cosmos, allowing astronomers to study these cosmic collisions and the properties of black holes in unprecedented detail. Post-merger, the newly formed black hole undergoes a ring-down phase, where any residual energy dissipates through gravitational waves, eventually settling down into a stable, rotating black hole. The entire process, from binary formation to merger, illuminates the complex and dynamic aspects of black hole physics, providing vital insights into the behavior of gravity in its most extreme form and the history of stellar evolution in the universe. Quasars are extraordinarily bright due to the intense activity occurring in their cores, where supermassive black holes reside. When a large amount of gas, dust, and other material falls into the gravitational well of a supermassive black hole, it doesn't just spiral straight in. Frictional forces within the accretion disk of infalling material heat it to extremely high temperatures. This process converts the gravitational energy of the infalling matter into significant electromagnetic radiation, primarily in the form of visible light, ultraviolet light, and X-rays, making quasars some of the most luminous objects in the universe. The process begins with the formation of an accretion disk around the supermassive black hole. As material in the disk spirals inward due to gravitational forces, intense friction and collisions among the particles generate tremendous heat, causing the disk to glow brightly. Some of the gravitational energy of the infalling material is thus converted into radiation. Additionally, the strong magnetic fields near the black hole can channel some of the hot gas into relativistic jets that shoot perpendicular to the disk. These jets also emit vast quantities of radiation across the electromagnetic spectrum. The sheer amount of material that is funneled into the black hole at a rapid rate allows quasars to outshine entire galaxies. In fact, a single quasar can be more luminous than all the stars in its host galaxy combined. Despite the vast distances, often billions of light-years, that separate us from these cosmic powerhouses, their brightness allows us to see them clearly, making them valuable tools for studying the early universe. Their extraordinary luminosity is a testament to the incredible energy conversion processes operating near supermassive black holes, providing critical insights into both black hole physics and galaxy evolution. Intermediate mass black holes, those with masses between 100 and 100,000 times that of our Sun, present an intriguing cosmic mystery. While stellar mass black holes arise from the gravitational collapse of massive stars, and supermassive black holes are found at the centers of galaxies, the pathway to forming these intermediate giants is less clear. One prevailing hypothesis suggests they form through the merging of smaller black holes and neutron stars in densely packed stellar environments, such as globular clusters. In these crowded settings, gravitational interactions can lead to frequent collisions and mergers between stellar remnants, gradually building up an object of intermediate mass. Another compelling theory posits that intermediate mass black holes could be the remnants of the very first stars, known as population 3 stars, which were incredibly massive and existed in the early universe. These primordial stars, lacking in heavier elements, could have collapsed directly into black holes with masses exceeding that of typical stellar mass black holes, thereby skipping some evolutionary phases. Additionally, gas accretion in young, dense star clusters can feed the growth of these black holes over time. These processes are supported by indirect evidence from X-ray emissions and gravitational wave detections, which hint at the existence of these elusive cosmic objects. Yet direct observation and confirmation remain a substantial challenge. Primordial black holes, theoretical remnants from the early universe, are a fascinating topic in cosmology. Unlike black holes that result from star collapse, these unique entities are believed to have formed shortly after the Big Bang, around 1 second later, due to extreme density fluctuations in the young cosmos. Depending on the precise nature and timing of these density peaks, primordial black holes could span a vast range of masses, from tiny subatomic scales to thousands of times the mass of our Sun. Some theories even suggest they might be a constituent of dark matter. What's particularly intriguing about primordial black holes is their potential role in cosmic phenomena. For instance, smaller primordial black holes with initial masses around that of a mountain could have evaporated by now due to Hawking radiation, a process theorized by physicist Stephen Hawking, where black holes emit radiation and lose mass over time. If any of these small black holes are still evaporating today, they might be detectable through bursts of high-energy gamma rays. On the other hand, larger primordial black holes, which did not fully evaporate, might still lurk in the universe, influencing cosmic structures and possibly being observed indirectly through their gravitational effects, such as microlensing events where their gravity distorts the light from stars behind them. This broad range of possible masses and behaviors highlights the elusive yet tantalizing nature of primordial black holes in our quest to understand the universe. Black holes have a profound effect on time, especially in their immediate surroundings, due to their immense gravitational pull. This phenomenon, known as gravitational time dilation, was predicted by Albert Einstein's theory of general relativity. Essentially, the stronger the gravitational field, the slower time moves relative to an observer in a weaker gravitational field. Near a black hole where gravitational forces are extreme, this effect becomes dramatically pronounced. Imagine an astronaut approaching a black hole. To a distant observer, the astronaut's clock would appear to tick increasingly slower as they approach the event horizon, the boundary beyond which nothing can escape the black hole's pull. If they were to remain stationary just outside the event horizon, time for them would almost come to a standstill compared to the distant observer. For the astronaut themselves, time would appear normal. They wouldn't notice any change in their own experiences. However, if they looked outwards, the universe around them would seem to speed up. Events that might take years in the far-off universe could seem to unfold in mere moments. This disparity in time perception is not just a theoretical musing, but has practical implications in astrophysics and space travel. The intense time dilation near black holes means that these regions offer natural laboratories for testing our understanding of gravity and the fabric of space-time itself. Observations of the behavior of matter near black holes, such as the accretion disks spinning at incredible speeds, also provide real-world evidence for these relativistic effects, reaffirming the mind-bending predictions of Einstein's theory. The spectacular jets emitted by some black holes, often seen bursting from the centers of active galaxies, are among the most enigmatic and energetic phenomena in the universe. These jets can extend tens of thousands of light-years into space, and their origins lie in the complex interplay of forces in the accretion disk around a black hole. When matter spirals into a black hole, it forms a dense, rapidly rotating disk known as an accretion disk. As this material moves inward, its gravitational potential energy is converted into heat and electromagnetic radiation, making the disk incredibly hot and luminous. The key to jet formation, however, is not just the accretion disk, but also the intense magnetic fields that are generated by the infalling material. These magnetic fields can twist and become wound up by the rotational energy of the black hole and the accretion disk. Through a process known as the Blanford-Znajek mechanism, energy is extracted from the rotation of the black hole and transferred to the magnetic fields, which then accelerate particles along the black hole's rotational axis at nearly the speed of light. This results in the narrow, focused beams of particles and radiation we observe as jets. Additionally, the interaction of these jets with the interstellar medium can create shock waves that further accelerate particles, producing high-energy emissions detectable across a range of wavelengths, from radio waves to gamma rays. These jets can affect their galactic environment on massive scales, influencing star formation and the distribution of matter. Thus, while the central engines driving these jets are compact and small, their influence extends far into the surrounding universe, offering a dramatic illustration of the raw power of black holes. Detecting gravitational waves from black hole mergers involves one of the most sensitive and sophisticated scientific instruments ever created, the Laser Interferometer Gravitational Wave Observatory, better known as LIGO, and its counterparts like the Virgo Observatory. Gravitational waves are ripples in the fabric of spacetime predicted by Albert Einstein's theory of general relativity. When massive objects like black holes spiral toward each other and merge, they generate these waves, which travel outward at the speed of light, stretching and compressing spacetime as they go. LIGO and Virgo detect these waves by using interferometry. Essentially, they consist of two long arms, each several kilometers in length, arranged in a perpendicular L shape. A laser beam is split into two, with each beam traveling down one arm, reflecting off mirrors at the ends, and then recombining. Under normal conditions, the beams are arranged so that they cancel each other out when they recombine. However, if a gravitational wave passes through, it will slightly alter the lengths of the arms, one arm getting compressed while the other stretches. This minute change disturbs the laser beam pattern, creating a detectable signal that indicates a gravitational wave has passed through. These changes in distance are fantastically small, on the order of 1/10,000th the diameter of a proton. To achieve this level of precision, these observatories operate in extreme conditions with advanced vibration isolation systems to eliminate noise and interference. When LIGO made its first detection in September 2015, it confirmed the merger of two black holes approximately 1.3 billion light-years away. The waveform recorded matched predictions from general relativity, showcasing the spiraling in spiral, merger, and eventual ring-down phase as the black holes coalesced. Since then, numerous additional detections have been made, offering new insights into the frequency and characteristics of black hole mergers, as well as opening a new era in astrophysics where we can study cosmic events through the medium of gravitational waves, providing a previously inaccessible window into the most violent and energetic events in the universe. White holes are theoretical cosmic objects that are essentially the opposite of black holes. While black holes are regions of space where nothing can escape once crossed the event horizon, white holes are proposed regions where matter and energy can only exit and nothing can enter. According to the equations of general relativity, white holes are mathematically possible, but no physical evidence of their existence has ever been observed. They remain largely in the realm of theoretical physics and speculation. If you were to encounter a white hole, the experience would be radically different from falling into a black hole. As you approached a white hole, you would be met with an incomprehensible barrage of energy and particles being ejected at near the speed of light. These emissions would create such a hostile environment that approaching a white hole closely would likely be impossible for any form of matter, let alone a human being. Assuming you somehow managed to avoid this lethal onslaught and reach the event horizon of the white hole, you would find yourself unable to move any closer. The laws of physics as we understand them dictate that no matter or energy can enter a white hole, meaning you would be perpetually repelled from its event horizon. Theoretically, should the concept of a white hole indeed manifest in the universe, it would present a fascinating enigma tied deeply to the fabric of spacetime itself. Some physicists speculate that white holes could be connected to black holes via wormholes, creating tunnel-like passages across the universe. This interplay of exotic theoretical entities leads to intriguing possibilities, like the potential for white holes to be observed in hypothetical high-energy cosmic events, though such phenomena remain speculative without empirical evidence. The study of these and other extreme objects continues to push the boundaries of our understanding of the universe, compelling us to challenge and rethink the fundamental laws of nature. Tabby's star, also known as KIC 8462852, has baffled astronomers with its peculiar dimming patterns. First identified by citizen scientists examining data from the Kepler Space Telescope, Tabby's star exhibits irregular and significant dips in brightness, unlike any other star observed. While the star's light flux can drop by up to 20%, these dimming events don't conform to the predictable patterns seen with planets transiting in front of a star, leading to wild speculations and multiple hypotheses. One of the leading theories involves an uneven dust cloud orbiting the star. These dust particles might be of varying sizes, causing the observed irregular dips when they block the light. Another hypothesis suggests that a disrupted cometary family, possibly due to a gravitational encounter, is passing in front of the star and blocking its light intermittently. Some even propose that the star could be surrounded by a large number of fragments from a disintegrated planet or a moon, creating the observed mysterious dimming. Despite these natural explanations, the mystery once led to speculation about the possibility of an alien megastructure, like a Dyson sphere, partially obstructing the star's light. While intriguing, this idea remains highly speculative with no supporting evidence thus far. Ongoing observations and research continue to aim at unraveling this cosmic riddle, making Tabby's star a focal point for both professional and amateur astronomers. Hypervelocity stars, those rogue stars barreling through space at speeds that can exceed 1 million miles per hour, owe their extraordinary velocities to some of the most powerful gravitational engines in the universe. Many of these cosmic speedsters originate from the heart of our galaxy, near the supermassive black hole known as Sagittarius A star. Situated about 26,000 light-years from Earth, Sagittarius A star has a mass equivalent to 4 million suns, generating an immense gravitational pull. One plausible mechanism for the acceleration of hypervelocity stars involves binary star systems that venture too close to this behemoth. As the pair of stars orbit each other, Sagittarius A star's formidable gravity can disrupt their delicate dance. In a dramatic celestial slingshot effect, one star may end up being gravitationally captured by the black hole, while its partner is flung outward at an exceptionally high velocity. The energy from the black hole dramatically accelerates the star, propelling it out of the galactic core and sending it zooming across the Milky Way. Another mechanism might involve interactions within dense star clusters. In these crowded environments, stars can engage in close gravitational encounters, where one star in a binary system can gain additional velocity through complicated three-body interactions and be ejected out of the cluster. Whether being slingshot by a supermassive black hole or launched through stellar jostling, hypervelocity stars provide a fascinating glimpse into the dynamic processes that shape our galaxy. Boyajian's star, often referred to as the WTF star, an abbreviation from Where's the Flux, presents another layer of cosmic curiosity with its unpredictable and fascinating dimming behavior. Unlike other stars whose brightness changes can often be attributed to regular, predictable causes, Boyajian's star, KIC 8462852, exhibits erratic drops in luminosity, leaving scientists to hunt for explanations. The leading hypothesis attributes these variations to a complex cloud of dust orbiting the star. Unlike a solid orbiting planet that would cause a uniform dimming event, these dust particles are uneven in size and density, leading to the pronounced and irregular dips in starlight. Some models suggest that this dust could originate from a disintegrating comet or a series of comets, transitioning to form an uneven dust envelope around the star. Adding to the intrigue, infrared observations have detected less heat emission than would be expected if solid objects like asteroids or planetary debris were the cause, leading scientists to favor the dust explanation. Moreover, the star's periodic brightening could be attributed to these cometary fragments clearing out or moving into positions that allow more light to escape intermittently. This interplay of orbital mechanics and light absorption by dust grains creates a dynamic situation where Boyajian's star sometimes shines brighter before another dip occurs. Despite the progress in understanding these phenomena, Boyajian's star remains a celestial enigma, continuously challenging astronomers to piece together the puzzle of its fluctuating luminosity. The discovery of galaxies that appear to lack dark matter has intrigued astronomers, as dark matter is traditionally considered a vital component in the formation and stability of galaxies. Dark matter, an unseen and mysterious substance, is believed to make up about 85% of the universe's mass, providing the gravitational framework necessary for galaxies to form and hold together. One example of a galaxy seemingly devoid of dark matter is NGC 1052 DF2, observed in 2018. Its unique characteristics have prompted scientists to reconsider how galaxies can form. The current hypothesis suggests a couple of intriguing possibilities. One idea revolves around the role of baryonic matter, or regular matter like gas and stars, interacting in a way that could mimic the effects typically attributed to dark matter. In this scenario, regular matter could have clumped together due to intense gravitational interactions with neighboring galaxies or through a high-velocity collision, leaving behind a galaxy that appears dark matter deficient. Another theory posits that such galaxies form within a unique environment. In dense galaxy clusters, intense gravitational forces can strip away the outer dark matter halo of smaller galaxies, leaving behind a dark matter-poor remnant. Additionally, interactions with other galaxies, such as tidal forces during close encounters, might expel dark matter while retaining the baryonic core. These processes could result in a galaxy like NGC 1052 DF2, where the observed motions of stars and gas do not require additional dark matter to explain their dynamics. These unexpected findings challenge scientists to refine existing models of galactic formation and distribution of dark matter, pushing the boundaries of our understanding of the cosmos. The study of these atypical galaxies continues to be a vibrant and rapidly evolving frontier in modern astrophysics. Oumuamua, the first known interstellar object to pass through our solar system, has captivated scientists and the public alike with its unusual properties and behavior. Discovered in October 2017 by astronomers at the Pan-STARRS 1 telescope in Hawaii, Oumuamua surprised researchers from the outset due to its cigar-like shape, approximately 10 times longer than it is wide, which is unlike any object previously observed in our solar system. Initially classified as a comet, Oumuamua showed no signs of the typical cometary activity such as a glowing coma or tail, which are caused by ice sublimating into gas as they approach the Sun. Further observations reclassified it as an asteroid. However, its velocity and trajectory through the solar system told another story. As Oumuamua sped away from the Sun, it exhibited an unexpected acceleration that couldn't be completely explained by gravitational forces alone. This unusual acceleration led to multiple theories attempting to explain the anomaly. One leading theory is that Oumuamua's acceleration could be due to outgassing, jets of gas releasing from its surface due to solar heating. However, the absence of detectable gas or dust components during its pass close to the Sun makes this explanation less likely. Another hypothesis suggests that Oumuamua might be a fragment of a larger object that was torn apart by gravitational forces, giving it a high aspect ratio and causing it to behave unexpectedly. Adding to the intrigue, some scientists speculated about the possibility of it being an artificial object, perhaps even a probe from an advanced alien civilization, although this remains highly speculative with no supporting evidence. Oumuamua's peculiarities have certainly spurred interest in interstellar visitors, highlighting the need for more data and observations to comprehend fully these enigmatic celestial travelers. Scientists eagerly await the next interstellar object that might pass through our solar system, hoping to unravel mysteries that Oumuamua has left in its wake. The intriguing phenomenon of subsurface oceans on certain planets and moons raises fascinating questions about the conditions necessary to sustain liquid water beneath icy exteriors. In our solar system, moons like Europa, Enceladus, and Titan are prime examples, each harboring vast oceans beneath their frozen crusts. The key to maintaining these hidden oceans lies primarily in the heat generated from tidal forces and, to a lesser extent, radioactive decay within their interiors. Take Europa, one of Jupiter's moons, for instance. Jupiter's immense gravity exerts significant tidal forces on Europa as it orbits, causing the moon's interior to flex and create frictional heat. This process, known as tidal heating, prevents the water beneath Europa's icy surface from freezing completely, keeping it in a liquid state. Enceladus, a smaller moon of Saturn, exhibits similar characteristics. Its icy surface features cryovolcanoes that spew water vapor and organic compounds, hinting at a subsurface ocean maintained by tidal interactions with Saturn and other nearby moons. Additionally, internal heat from the decay of radioactive elements within these moons' rocky cores contributes to maintaining their subsurface oceans. On Titan, Saturn's largest moon, the situation is slightly different. Titan has a thick atmosphere composed mostly of nitrogen and methane, which creates a substantial greenhouse effect, trapping heat that helps sustain a subsurface ocean beneath its icy crust. These subsurface oceans are not only a marvel of planetary science, but also a tantalizing prospect for the search for extraterrestrial life. The liquid water environments, shielded from harsh surface conditions, could potentially harbor microbial life or other forms of simple organisms. Future missions like Europa Clipper and the Enceladus Life Finder aim to probe these hidden waters more closely, hoping to uncover the secrets beneath the ice and broaden our understanding of where life might exist in the cosmos. The mysterious flashes of light observed on the moon's surface, often termed transient lunar phenomena, TLP, have puzzled astronomers for centuries. These transient events can range from momentary bright spots to brief glowing or colorful glows on the lunar surface, lasting anywhere from seconds to a few minutes. While the exact causes of these phenomena remain somewhat elusive, several compelling explanations have been proposed based on contemporary observations and studies. One prominent theory involves the interaction of the moon's surface with meteoroids. When small meteoroids and cosmic debris collide with the moon at high velocities, they generate enough kinetic energy to produce brief flashes of light, visible from Earth. Unlike Earth, The Moon lacks an atmosphere to burn up these incoming objects, leading to frequent and unobstructed impacts that can produce observable light bursts. Another explanation suggests that lunar outgassing could be responsible for some of these mysterious flashes. This process involves the release of gas from beneath the Moon's surface, potentially due to tidal stresses caused by the gravitational pull of the Earth. When these gases escape, they could interact with the lunar dust or simply fluoresce in the vacuum of space, producing a temporary glow or flash. Electrostatic phenomena have also been proposed as a potential cause. The Moon's surface is coated with a layer of fine electrostatically charged dust that can be disturbed by solar radiation or the solar wind. As these particles are displaced or levitated, they can reflect sunlight in varying ways, creating brief, glimmering flashes. While no single theory can account for all observed TLP events, ongoing lunar missions and telescopic monitoring aim to gather more data. For instance, lunar orbiters equipped with high-resolution cameras and spectrometers continue to observe and record these occurrences, providing scientists with critical insights into the dynamic processes at play on our celestial neighbor's surface. The study of TLP not only intrigues those fascinated by lunar phenomena, but also enhances our broader understanding of the Moon's geologic and impact activity. Stars defying the models of stellar evolution present a fascinating challenge to our understanding of astrophysics, compelling scientists to rethink and refine their theories. One prominent example is the blue straggler stars found in globular clusters. According to conventional models of stellar evolution, stars within these densely packed clusters should be old, red, and nearing the end of their life cycles. However, blue stragglers stand out as anomalous. They are hotter, bluer, and seemingly younger than their stellar neighbors. One leading hypothesis to explain blue stragglers involves stellar collisions or mergers within the dense environments of globular clusters. In these crowded conditions, close encounters between stars are relatively common. When two stars collide or merge, they can form a more massive single star that appears rejuvenated. This newly formed star burns hotter and bluer, looking much younger than the cluster's average age. Another intriguing case is the existence of ultramassive, highly luminous stars, known as Wolf-Rayet stars, which don't fit neatly into the conventional life cycle models. These stars, thought to be in a late stage of stellar evolution, have lost most of their outer hydrogen layers, exposing their hotter helium-burning cores. The reason for such extensive mass loss could be attributed to intense stellar winds driven by their extreme luminosity and high surface temperatures. These winds expel material at rates thousands of times greater than those of typical stars, leading to drastic changes in their structure and evolution. Additionally, certain stars exhibit unusual compositions that defy existing models. For example, carbon-enriched metal-poor stars challenge the understanding of nucleosynthesis processes in the early universe. These stars display surprisingly high levels of carbon compared to other heavy elements, indicating complex, poorly understood processes in the first generations of stars. These stellar oddities underscore the complexity and diversity of star formation and evolution processes. They compel astronomers to refine existing models and consider alternative pathways in stellar evolution. As observational technology advances, providing better data and higher resolution, these anomalies will continue to be pivotal points of study, pushing the boundaries of our cosmic knowledge. The thermosphere, one of the outer layers of Earth's atmosphere, experiences significant and seemingly inexplicable temperature variations that have piqued the curiosity of scientists. Sitting above the mesosphere and stretching from about 50 miles to several hundred miles above the Earth's surface, the thermosphere is characterized by fluctuations that can range from approximately 500 degrees Fahrenheit to over 2,000 degrees Fahrenheit. These variations are driven by several dynamic factors, including solar activity, geomagnetic storms, and the complex interactions between charged particles and atmospheric gases. A primary driver of temperature changes in the thermosphere is solar activity, particularly variations in solar ultraviolet, UV radiation, and X-rays. During periods of high solar activity, such as solar flares and coronal mass ejections, there is an influx of high-energy radiation that increases the thermosphere's temperature. This additional energy ionizes the sparse gases in this layer, causing them to move more vigorously and heat up. Conversely, during periods of low solar activity, the reduced solar radiation results in cooler temperatures. Another vital factor contributing to these temperature variations is geomagnetic storms, which are disturbances in Earth's magnetosphere caused by solar wind and solar energetic particles. When these charged particles interact with Earth's magnetic field, they can be directed towards the polar regions, where they enter the atmosphere and generate auroras. This activity deposits significant amounts of energy into the thermosphere, leading to localized heating. Additionally, the thermosphere's temperature is influenced by the dynamic interactions between atmospheric gases and charged particles. As particles in the ionosphere, part of the thermosphere, collide, they can energize gas molecules, contributing to temperature changes. The vertical motion of atmospheric waves from lower atmospheric layers also plays a role, transferring energy upwards and causing temperature fluctuations. The interplay of these factors creates a complex, ever-changing environment in the thermosphere. These temperature swings have practical implications, affecting satellite orbits and communication systems. As observational technologies and climate models improve, scientists aim to gain a deeper understanding of these processes, enhancing our ability to predict and mitigate the impacts of thermospheric temperature variations. The enduring spiral structures of galaxies present a captivating puzzle that astronomers have studied for decades. These grand designs, gracefully sweeping across the cosmos, are not static. They are dynamic patterns maintained by complex gravitational and hydrodynamic processes. A fundamental aspect of understanding how these galaxies, such as our own Milky Way, preserve their spiral arms for billions of years involves the interplay between stars, interstellar gas, and dark matter. One of the leading theories explaining the persistence of spiral arms is the density wave theory. According to this theory, spiral arms are not composed of the same stars and gas over time, but are rather regions of higher density that move through the galaxy. Think of spiral arms as traffic jams on a cosmic scale. Just as cars in a traffic jam move in and out of the jam, stars and gas in spiral arms are not permanent residents. They move in and out of these denser regions. As stars and gas enter these areas of higher density, they slow down and compress, intensifying star formation and making the arms more pronounced. This density wave moves through the galaxy's disk, perpetuating the spiral structure. Another factor contributing to the maintenance of spiral structures is the gravitational interactions within the galaxy and with nearby galaxies. Gravitational torques and resonance effects can amplify and sustain spiral arm features. Bars in galaxies, which are elongated central features, can also drive the formation of spiral arms. The gravitational influence of a bar can induce spiral density waves in the disk, reinforcing the spiral structure. The role of dark matter, which makes up a significant portion of a galaxy's mass, cannot be underestimated. The dark matter halo surrounding a galaxy provides additional gravitational stability, helping to sustain the rotation curve that supports the spiral structure. This stabilizing effect helps maintain the galaxy's overall shape and the persistence of its spiral arms over cosmological timescales. Understanding these processes has been enhanced by advanced computer simulations and observational technologies. These tools allow scientists to model the intricate gravitational and hydrodynamic interactions that sustain spiral arms. Ongoing research continues to delve into these mechanisms, seeking to unravel the detailed orchestration of forces that enable spiral galaxies to retain their iconic structures over billions of years, enriching our cosmological narrative. Protecting astronauts from cosmic radiation during long-duration spaceflights presents one of the most formidable challenges in human space exploration. Cosmic radiation, composed of charged particles from the Sun and beyond our solar system, can pose significant health risks, including increased cancer risk, damage to the central nervous system, and acute radiation sickness. As space agencies plan missions to Mars and beyond, developing effective strategies to mitigate this radiation exposure becomes crucial. One approach involves shielding, utilizing materials that can absorb or deflect incoming radiation. Traditional materials like aluminum, commonly used in spacecraft construction, provide some protection. However, researchers are exploring more effective alternatives such as polyethylene, which contains hydrogen atoms that are efficient at blocking particle radiation. Advanced composites and novel materials, including high-density polymers and hydrogen-rich substances like borated polyethylene, offer enhanced shielding properties and are being tested for their practicality in spacecraft design. Water is another promising shielding material due to its high hydrogen content and versatility. It can serve dual purposes as a protective barrier and a vital resource for astronauts. Placing water tanks around crew habitats can create a protective shield, reducing radiation exposure. In addition, engineers are investigating the potential of using waste materials generated during the mission as shielding, maximizing resource utilization and enhancing protection. Beyond passive shielding, magnetic and electric fields offer innovative protective solutions. Inspired by Earth's magnetosphere, which shields our planet from cosmic radiation, scientists are researching the viability of creating artificial magnetic fields around spacecraft. These fields would deflect charged particles away from the spacecraft, mimicking the natural protection we experience on Earth. Similarly, electrostatic shielding could repel charged particles, offering another layer of defense. Advanced monitoring and early warning systems also play a pivotal role in protecting astronauts. Real-time radiation detection and forecasting can alert astronauts to increased radiation levels from solar events, allowing them to take refuge in specially shielded areas of the spacecraft. These storm shelters, designed with enhanced shielding, can provide temporary protection during solar particle events. Lastly, pharmacological countermeasures are being explored to protect against radiation damage. Radioprotective drugs that mitigate the effects of radiation on the human body are a burgeoning area of research, aiming to reduce the biological impact of radiation exposure. By combining these various strategies, advanced materials, innovative shielding concepts, real-time monitoring, and pharmacological aids, scientists hope to develop robust protection systems for astronauts embarking on long-duration missions. This multifaceted approach is essential to ensuring the safety and success of future interplanetary travel as we push the frontiers of human exploration deeper into the cosmos. Establishing a permanent base on Mars involves overcoming a multitude of formidable challenges, encompassing technological, environmental, physiological, and psychological hurdles. Each obstacle requires innovative solutions and considerable resources to ensure the safety, sustainability, and productivity of human settlers on the Red Planet. One of the primary challenges is the harsh Martian environment. Mars's thin atmosphere, composed mainly of carbon dioxide, lacks sufficient oxygen and offers little protection from harmful solar and cosmic radiation. This necessitates the development of habitats with robust shielding to protect inhabitants from radiation and extreme temperature fluctuations, which can range from a temperate 70 degrees Fahrenheit to a frigid -100 degrees Fahrenheit. Additionally, dust storms on Mars can envelop the entire planet and last for weeks, posing risks to both systems and humans. Another significant challenge is providing the essentials of life: air, water, and food. Water, although present as ice and potentially in subsurface reservoirs, needs to be efficiently extracted, processed, and recycled. Oxygen production for breathing and as fuel for spacecraft must be managed through technologies such as electrolysis of water or chemical processes that convert carbon dioxide from the atmosphere into oxygen. For food, growing crops in Martian soil, which contains toxic perchlorates, would require either soil treatment or development of hydroponic or aeroponic systems within controlled environments. The extreme distance from Earth, averaging about 140 million miles, complicates communication and supply lines. Communication lag, which can be up to 24 minutes for a round trip, makes real-time conversations impossible and requires autonomous systems to perform critical functions. Resupply missions would be expensive and infrequent, necessitating a high degree of self-sufficiency among the settlers. Repairing equipment and producing materials on Mars, known as in-situ resource utilization, becomes crucial for sustainability. This involves utilizing Martian resources to create building materials, tools, and even fuel. Physiologically, humans must contend with reduced gravity, about 38% of Earth's, which affects muscle and bone density, cardiovascular function, and overall health. Long-term exposure to microgravity during the journey and the lower gravity on Mars requires ongoing medical and exercise regimes to mitigate health risks. Psychological challenges are also significant, as astronauts will face isolation, confinement, and the stress of living in a hostile environment far from Earth. Considering the multifaceted nature of these challenges, international collaboration, sustained investment in research and technology development, and iterative testing through missions to the Moon and low Earth orbit habitats are essential. Ensuring the success of a permanent Mars base will require meticulously addressing these obstacles, leveraging advancements in science and engineering, and fostering the resilience and adaptability of human pioneers. Making interplanetary travel more efficient is a multifaceted endeavor that involves advancements in propulsion technology, resource management, spacecraft design, and mission planning. Each of these components plays a critical role in reducing the time, cost, and risks associated with traversing the vast distances between planets. One of the most promising avenues for enhancing the efficiency of interplanetary travel is the development of advanced propulsion systems. Traditional chemical rockets, while effective for launching payloads out of Earth's gravity well, are not ideal for the long-duration, high-speed journeys required for interplanetary missions. Alternative propulsion technologies, such as electric propulsion, ion thrusters, offer significant advantages. Ion thrusters use electricity, often generated by solar panels, to ionize a propellant, like xenon, and expel it at high speeds. Although they produce lower thrust compared to chemical rockets, they are far more efficient, allowing spacecraft to reach higher speeds over extended periods. Another breakthrough technology is nuclear thermal propulsion, which uses a nuclear reactor to heat a propellant like hydrogen. The heated hydrogen then expands rapidly and is expelled to generate thrust. This method can provide much greater efficiency and higher specific impulse than chemical rockets, potentially cutting travel times to Mars and other destinations significantly. Even more advanced concepts, such as nuclear electric propulsion, combine the benefits of nuclear thermal propulsion with electric thrusters, potentially offering even higher efficiencies and propulsion capabilities. Resource management is another critical area. The concept of in situ resource utilization aims to use materials found on other celestial bodies to produce fuel, water, oxygen, and building materials. By reducing the need to carry all supplies from Earth, in situ resource utilization can significantly decrease mission costs and launch mass, making long-term missions more feasible. For example, extracting water ice from Mars or the Moon and converting it into hydrogen and oxygen for fuel or life support could revolutionize mission logistics. Efficient spacecraft design also plays a crucial role. Innovations in lightweight materials such as advanced composites and alloys can reduce the mass of spacecraft, improving fuel efficiency and payload capacity. Modular spacecraft design allows for parts to be assembled in space, eliminating the need to launch a fully built, heavy spacecraft from Earth. This modularity also enhances the versatility and reusability of space habitats and vehicles. Mission planning and trajectory optimization can further increase efficiency. Utilizing gravitational assists from other planets can slingshot spacecraft to higher speeds without additional fuel expenditure. Advanced software algorithms can calculate precise trajectories that minimize travel time and fuel use, leveraging the gravitational fields of celestial bodies to the spacecraft's advantage. Incorporating artificial intelligence, AI, and automation can streamline mission operations. AI can assist with real-time decision-making and autonomous navigation, reducing dependency on Earth-based control and enabling quicker responses to unforeseen challenges. Lastly, international collaboration can pool resources, knowledge, and technology, distributing the immense costs and technical demands of interplanetary travel. Agencies like NASA, ESA, Roscosmos, and private companies like SpaceX and Blue Origin are already making strides in collaborative efforts, building a more sustainable framework for future space exploration. By integrating these advancements, interplanetary travel will not only become more efficient, but also safer and more sustainable, paving the way for humanity's expansion into the solar system and beyond. Mining asteroids, often touted as the next frontier in space exploration and resource acquisition, requires a suite of advanced technologies. These technologies must address a range of challenges, from locating and accessing asteroids to extracting and processing valuable materials. The potential rewards include access to rare metals, water, and other resources that could support space settlements and activities. First and foremost, prospecting technologies are essential. Detailed and accurate reconnaissance of asteroids is necessary to identify those with the highest potential for valuable resources. Sophisticated space telescopes like NASA's NEOCAM or ESA's HERA mission play a crucial role in surveying and cataloging asteroids. Once potential targets are identified, detailed mapping using spectrometers and radar instruments on reconnaissance missions can provide data on an asteroid's composition, structure, and surface characteristics. Upon selecting a target, the next step involves developing spacecraft capable of reaching and attaching to an asteroid. This requires advanced propulsion systems, such as ion thrusters or nuclear thermal propulsion, that can efficiently travel to and maneuver around these small celestial bodies. Capture mechanisms like robotic arms or harpoons must be designed to latch onto the irregular surfaces of asteroids in the low-gravity environment. Mining technologies must be capable of extracting materials in the challenging conditions of space. For example, autonomous mining robots and drills can excavate the surface and subsurface materials. One promising technique is regolith heating, where concentrated solar energy or microwave technology heats the asteroid material to release volatile compounds such as water. Another technique involves mechanical excavation using drills and cutters designed to operate in microgravity. These systems must be robust, yet delicate enough to handle the often brittle and loosely bound material found on asteroids. Processing the extracted materials on site or in a nearby space facility is another major technological hurdle. In situ resource utilization, ISRU technologies, could purify and convert raw materials into usable forms. For instance, extracted water can be split into hydrogen and oxygen through electrolysis, providing life support or rocket fuel for further missions. The processing of metals and other valuable compounds into more refined materials for use in space manufacturing or construction can involve melting and recasting using solar furnaces or other space-based processing facilities. Storage and transportation of mined resources are also significant challenges. Technologies must be developed to safely contain and transport volatile materials in space. Container systems that can handle the microgravity and vacuum of space, as well as protect the materials from contamination or loss, are essential. Efficient spacecraft designed to ferry these materials back to Earth or other destinations within the solar system must be developed, incorporating reliable re-entry systems if returning to Earth. Advanced automation, robotics, and artificial intelligence, AI, will play critical roles throughout the mining process. Autonomous systems can operate with minimal human intervention, reducing the need for crewed missions and allowing continuous operation. AI can enhance the efficiency of resource extraction and processing by optimizing operations and managing unforeseen challenges. Finally, regulatory and legal frameworks must be established to govern asteroid mining activities. International agreements and guidelines will be necessary to ensure that resources are utilized responsibly and equitably, fostering cooperation rather than competition. By addressing these technological, logistical, and legal challenges, the dream of mining asteroids can move closer to reality, opening up new horizons for resource acquisition and the future of space exploration and economy. Developing sustainable life support systems for space colonies hinges on creating closed-loop ecosystems that can replicate Earth's resources over extended periods. At their core, these systems must integrate reliable methods for air purification, water recycling, and food production. Scientists are exploring the use of bioregenerative systems where plants not only provide food, but also play critical roles in oxygen generation and carbon dioxide absorption. For instance, a greenhouse module equipped with carefully selected crops could potentially convert human carbon dioxide into oxygen through photosynthesis, simultaneously offering nutrition. Such an approach would require meticulous planning, as around 750 grams of plant biomass are needed daily per person to maintain oxygen levels comparable to those on Earth. In parallel, recycling water within these colonies is essential to reduce the need for resupply missions from Earth. Advanced filtration and purification technologies, such as forward osmosis and distillation, can transform wastewater back into clean, drinkable water. NASA has been working on systems that can achieve upwards of 95% water recovery from all available sources, including urine. Moreover, integrating microbial life in bioreactors might further enhance the decomposition of waste, turning it back into usable resources. This pursuit of efficiency must also include ways to conserve and reuse materials to construct and maintain habitats, ensuring that these colonies can thrive independently in the boundless and harsh expanse of space. The prospects for space-based solar power are becoming increasingly promising as technological advancements and economic considerations converge. Space-based solar power involves the deployment of large arrays of solar panels in Earth's orbit that can capture solar energy continuously, without the interruptions faced by ground-based systems due to weather or the day-night cycle. This energy would then be transmitted back to Earth via microwave or laser beams, where it could be converted into electricity. One of the most compelling advantages of space-based solar power is its potential for uninterrupted, constant energy generation. A single square meter of space solar panels can hypothetically yield up to 13 times more energy compared to the same area on Earth, due to the absence of atmospheric interference. Engineers and scientists are tackling the formidable challenges associated with this ambitious endeavor. Critical to the success of space-based solar power is reducing the cost of launching and assembling these massive structures in orbit. The advent of reusable rockets, like those developed by SpaceX, promises to lower launch costs significantly, making the deployment of large-scale solar arrays more feasible. Moreover, advancements in materials science are leading to lighter and more efficient solar panels, boosting the overall energy return on investment. Yet there remain substantial hurdles, such as the efficient transmission of energy back to Earth and ensuring the safety and reliability of these systems. While practical deployment might still be a few decades away, current research and prototypes suggest that space-based solar power could one day provide a substantial share of the world's energy needs, contributing to a more sustainable and carbon-neutral future. Improving long-distance space communication requires overcoming significant technical challenges, primarily related to the vast distances and signal degradation over time and space. One promising avenue is the use of laser-based communication systems, which offer significant advantages over traditional radio frequency methods. Lasers can transmit data at rates up to 100 times faster than radio waves, and can also focus the communication beam more narrowly, significantly reducing signal dispersion. For instance, NASA's Laser Communications Relay demonstration aims to validate this technology, highlighting the potential for relaying vast amounts of data from distant spacecraft back to Earth with higher efficiency and lower latency. Another groundbreaking leap in space communication revolves around the development and deployment of quantum communication networks. Quantum entanglement, famously described by Einstein as spooky action at a distance, could enable instantaneous data transmission, theoretically allowing for real-time communication across vast distances. Quantum communication relies on entangled particles, which maintain a direct connection regardless of the space separating them. Altering the state of one particle instantaneously affects the other. Though still in the experimental stages, this approach could eventually bypass the current limitations imposed by the finite speed of light. To support these technological advancements, an infrastructural overhaul might be necessary, including the establishment of relay stations on the Moon, Mars, and potentially other strategic points throughout the solar system. These relays would act as interstellar waypoints, ensuring consistent and reliable data transfer. Combining these advanced communication techniques with robust and strategically positioned infrastructure could dramatically enhance our ability to operate and explore not just our solar system, but potentially interstellar spaces, thereby transforming our cosmic communications paradigm. Next-generation propulsion technologies are crucial for enabling deep space exploration, aiming to drastically reduce travel times and increase the efficiency of spacecraft. Ion propulsion is one of the leading candidates, already showcased in missions like NASA's Dawn spacecraft. This technology uses electric fields to accelerate ions, providing a steady and efficient thrust over long durations. Unlike traditional chemical rockets, which deliver a brief, powerful thrust, ion engines produce a low, continuous thrust, allowing spacecraft to achieve higher speeds over time. The most advanced ion thrusters can potentially propel missions to distant asteroids, Mars, and beyond with significantly less fuel. In addition, nuclear thermal propulsion is gaining renewed interest as a powerful method for deep space travel. Nuclear thermal propulsion uses nuclear reactions to heat a propellant, typically hydrogen, to high temperatures, which then expands and is expelled to produce thrust. This method could offer a dramatic improvement over chemical rockets, providing around twice the efficiency in terms of specific impulse. NASA, along with agencies like DARPA, is working on projects to demonstrate the feasibility and safety of nuclear thermal propulsion, potentially enabling crewed missions to Mars in the not-too-distant future. The capability to halve travel time to the Red Planet or other distant destinations could markedly improve mission viability and reduce risks to human explorers. Moreover, the concept of harnessing solar sails is advancing, leveraging photon pressure from the sun's rays to push spacecraft forward. The Japanese space agency's Icarus mission successfully demonstrated this technology, showing that it could be used for propulsion without the need for onboard fuel. Solar sails could enable missions to the outer planets and even interstellar space, utilizing the constant, albeit weak, push provided by sunlight, potentially augmented by laser propulsion systems from Earth's orbit for an initial boost. As these next-generation propulsion technologies evolve, the dream of deeper, faster, and more efficient space exploration edges closer to reality, unlocking new frontiers for human exploration and scientific discovery. Detecting and deflecting potentially hazardous near-Earth objects, NEOs, is essential to mitigate collision risks that could have catastrophic consequences for our planet. Advanced telescopic surveys are at the forefront of detection efforts, utilizing ground-based observatories equipped with wide-field cameras to regularly scan the skies. Projects like NASA's Near-Earth Object Wide-Field Infrared Survey Explorer have been particularly effective in identifying and characterizing NEOs. These telescopes can detect even relatively small asteroids, measuring as little as 30 meters in diameter, by capturing their infrared signatures, which are often more revealing than visible light. After detecting an NEO, scientists rely on precise tracking and orbital modeling to predict its trajectory and assess the probability of collision with Earth. If an object is found to pose a significant threat, planetary defense strategies come into play. One of the most researched methods for deflection is the kinetic impactor technique, where a spacecraft is deliberately crashed into the NEO to alter its course. NASA's double asteroid redirection test, for example, aims to demonstrate this technique by impacting the smaller body of the binary asteroid system Didymos. Another promising approach involves using gravity tractors, which entail stationing a spacecraft near the NEO. The spacecraft's gravitational pull gradually alters the object's trajectory over time, providing a non-invasive and controllable method of deflection. Additionally, more advanced concepts, though currently theoretical, include deploying solar sails on asteroids to exploit photon pressure for course correction, or even using concentrated solar energy to vaporize parts of the NEO's surface, creating a reactive thrust. As technology and our understanding of space improve, these combined efforts of detection and deflection form a comprehensive strategy to safeguard our planet from potential cosmic threats, ensuring that we can predict and, if necessary, prevent impacts well in advance. Building large structures in space presents a myriad of challenges, primarily due to the harsh environment and the constraints of operating in microgravity. One of the most significant hurdles is transporting materials and components from Earth to space. Traditional rockets have limited payload capacities, meaning that all construction materials must be light yet strong enough to withstand the stress of launch and the space environment. Innovations in lightweight materials, such as carbon fiber composites and advanced alloys, are crucial for overcoming this challenge. Moreover, the cost of lifting materials into space remains prohibitive, necessitating advanced methods of construction that utilize in-situ resources, such as 3D printing with lunar or asteroidal regolith. Microgravity also complicates construction processes that are straightforward on Earth. In space, traditional assembly techniques like welding and bolting can be problematic due to the lack of a stable workspace and the dispersion of materials. To address this, engineers are developing robotic systems that can autonomously or semi-autonomously perform assembly tasks. For instance, the European Space Agency's remote welding robot Cosmic Kiss is exploring how to securely join metal pieces in space. Additionally, NASA's Archinaut project aims to build and deploy large structures using robotic arms equipped with additive manufacturing capabilities. These robots can both fabricate parts and assemble them in orbit, drastically reducing the need for human spacewalks, which are both risky and resource-intensive. Another major challenge is ensuring the structural integrity and durability of space constructions. Space structures must withstand extreme temperature variations, radiation, and potential impacts from micrometeoroids. Advanced materials like multi-layer insulation and radiation-hardened composites are being developed to protect structures in these hostile conditions. Furthermore, creating livable habitats requires effective shielding from space radiation, reliable life support systems, and the ability to manage the accumulated stress from long-term space exposure. As these technologies advance, the dream of building substantial and sustainable structures in space, ranging from large telescopes and space stations to future human habitats on the Moon or Mars, becomes increasingly achievable. The search for life within our solar system primarily focuses on bodies that possess or once possessed the essential elements for supporting life as we understand it: liquid water, an energy source, and the right chemical ingredients. Among the most promising locations is Europa, one of Jupiter's moons. Europa is intriguing because of its subsurface ocean, which lies beneath an ice crust that is thought to be several kilometers thick. Evidence from the Galileo spacecraft and the Hubble Space Telescope suggests that this vast, hidden ocean could harbor the necessary conditions for life, particularly near hydrothermal vents on the ocean floor, where chemical interactions provide energy that could support microbial ecosystems, similar to those found around Earth's deep-sea vents. Saturn's moon Enceladus also captures scientists' interest, owing to its geysers that eject water vapor and organic molecules into space from a subsurface ocean. The Cassini spacecraft detected these plumes and analyzed their composition, finding salts and simple organics that imply hydrothermal activity on the seafloor. Such environments could provide the energy needed to sustain life. The discovery of these geysers makes Enceladus an attractive target for future missions aimed at sampling the ejected materials directly, potentially revealing signs of biological activity without the need to drill through its thick ice crust. Mars continues to be a focal point in the search for life, both past and present. The red planet boasts a more Earth-like environment in its history, with evidence of ancient river valleys, lake beds, and possibly even an ocean. Rover missions such as Curiosity and Perseverance are actively exploring these ancient sediments and clay-rich deposits that could harbor microbial life or at least fossilized remains. Mars also presents tantalizing possibilities for still-present life in its subsurface, where liquid water might exist. Recent radar data indicate the existence of salty, subsurface lakes, increasing the potential for niches where microbial life could survive. Even more speculative but equally exciting is the potential for life in the hydrocarbon lakes and seas of Triton, Saturn's largest moon. Titan's thick atmosphere and surface liquids, composed mainly of methane and ethane, offer an entirely different chemistry for life, one that would not be water-based. While any organisms on Titan would be unlike anything we know, the complexity and richness of its chemical processes make it a prime candidate for explorations that could redefine our understanding of life's potential. These celestial bodies, each with its unique set of conditions, propel our ongoing quest to discover life beyond Earth, guiding the design and focus of future exploratory missions. Defining and detecting biosignatures on exoplanets involves identifying specific chemical compounds, patterns, or phenomena that serve as indicators of life processes, which cannot be easily explained by non-biological means. Biosignatures can range from molecular oxygen and methane to more complex organic molecules like amino acids and proteins. One of the most promising biosignatures is the simultaneous presence of oxygen and methane in a planet's atmosphere. On Earth, these gases are continually produced by living organisms. Their co-presence would indicate ongoing biological activity because they react with each other and would not coexist naturally without constant replenishment. Advanced telescopes and spectroscopic techniques are fundamental in detecting these biosignatures. Instruments like the James Webb Space Telescope, JWST, and ground-based observatories equipped with high-resolution spectrometers analyze the light spectrum from distant planets as it passes through or is reflected from their atmospheres. This light can be broken down into its constituent wavelengths, revealing absorption lines that correspond to specific chemicals. For example, the absorption lines for oxygen appear at specific points in the spectrum, allowing scientists to infer its presence and concentration. The upcoming European Extremely Large Telescope, ELT, with its unprecedented light-gathering capacity, will further enhance our ability to detect and analyze these faint signals from exoplanets. However, interpreting these signals requires caution. Some biosignature gases can be produced through geological or photochemical processes. For instance, volcanic activity might release methane, and ultraviolet radiation can split water molecules into hydrogen and oxygen. Thus, the context of the planet's environment, including its geological and atmospheric processes, must be carefully evaluated. The study of these planets, or even better, multi-signature investigations where multiple potential biosignatures are detected together, provides stronger evidence of biological activity. Recent technological advancements have also led to considerations of technosignatures, indicators of advanced technological activity such as specific radio signals or laser emissions. Ultimately, while the detection of a single potential biosignature is promising, it's the combination of multiple lines of evidence, analyzed through various observational platforms and theoretical models, that will most convincingly suggest the presence of life on distant exoplanets. These interdisciplinary efforts merge the fields of astronomy, biology, chemistry, and planetary science to decode the complexities of life's potential in the cosmos. Detecting microbial life on other worlds presents a range of formidable challenges, primarily because of the difficulty in identifying definitive signs of life and differentiating them from abiotic processes. One major obstacle is the need to directly access the environments where microbial life might exist. For instance, subsurface biospheres on planets like Mars or the ice-covered oceans of moons like Europa and Enceladus are physically challenging to reach. Drilling through kilometers of ice or rock to obtain pristine samples without contamination from Earth-based organisms is a significant technical feat. Current technology constraints limit our ability to deploy autonomous drilling and sampling equipment that can operate efficiently in such extreme conditions. In addition to the physical barriers, the chemical signatures of microbial life are often subtle and can easily be confused with non-biological chemical reactions. For example, simple organic molecules like methane can be generated through geological processes, such as serpentinization, where water interacts with certain rock types. To confidently attribute such molecules to biological activity, a comprehensive understanding of the planet's geology is necessary, alongside advanced analytical instruments capable of distinguishing between biotic and abiotic origins. Rovers like Perseverance on Mars carry sophisticated suites of instruments to analyze soil and rock samples, but the interpretation of the results often hinges on complex models that factor in the planet's entire chemical context. Furthermore, the limitations of remote sensing technology add another layer of complexity. While instruments aboard spacecraft can conduct in situ measurements, the sensitivity and specificity required to detect microbial life at a distance, especially on exoplanets, remain beyond current capabilities. Remote detection requires highly sensitive spectrometers and other tools to identify faint biosignatures from millions or even billions of kilometers away. Additionally, the microbial life we're searching for might not use the same biochemistry as terrestrial life, complicating our search efforts further. There's the possibility that alien microbes could utilize exotic biochemical pathways that we haven't conceived yet, making our Earth-centric detection methods ineffective. Finally, contamination is a perennial concern. Introducing even trace amounts of terrestrial microbes can compromise the integrity of samples and lead to false positives. Stringent planetary protection protocols are in place, such as those practiced by NASA and ESA. But ensuring absolute sterility amidst the unpredictable conditions of space exploration is exceedingly difficult. Overcoming these challenges requires ongoing technological innovation, rigorous scientific methodology, and meticulous planning of missions to maximize the chances of detecting genuine signs of extraterrestrial microbial life, while minimizing the risks of contamination and misinterpretation. Life evolving on a planet orbiting a red dwarf star would face a unique set of environmental challenges and conditions, leading to potentially fascinating adaptations and evolutionary paths. Red dwarfs, which are cooler and smaller than our Sun, emit less light and heat, which means that their habitable zones, the regions where liquid water could exist, are much closer to the star. This closer proximity exposes the planet to higher levels of stellar activity, including intense solar flares and increased ultraviolet radiation. For life to thrive under such conditions, it might need robust mechanisms for radiation protection, such as thicker atmospheres rich in protective gases like ozone, or it might reside underground or underwater to shield from harmful radiation. The lower energy output of red dwarfs means that life-supporting planets would receive less sunlight. Photosynthetic organisms, if they exist, would have to adapt to these lower light levels. They might evolve to use a broader spectrum of light, including infrared, which is more abundant around red dwarfs. Terrestrial algae and bacteria, for example, demonstrate this versatility on Earth by utilizing different pigments to capture light across various wavelengths, suggesting that alien organisms could develop similar or even novel pigments to maximize energy capture. Additionally, the closer orbit and tidal locking, a situation where one hemisphere always faces the star while the other remains in perpetual darkness, could result in vastly different environmental conditions on each side of the planet. Life forms might adapt to these extremes, with hardy organisms in the twilight zones where conditions are relatively stable. Furthermore, the longevity of red dwarfs could influence evolutionary timelines. These stars can burn steadily for tens to hundreds of billions of years, providing a stable energy source far longer than our Sun. This lengthy period could allow life more time to develop and evolve complexity. The evolution of intelligence and advanced civilizations could have a higher likelihood given the extended timescales, provided the environmental pressures are not excessively harsh. However, the frequent stellar flares of young red dwarfs could strip away planetary atmospheres or lead to extreme environmental fluctuations. Life might evolve quickly to adapt to these changes or develop symbiotic relationships that offer mutual protection and resilience. Alternatively, if the flares are too violent, life might be restricted to subsurface niches or other protective environments. While the conditions on a planet orbiting a red dwarf star would be challenging, they could foster unique evolutionary trajectories. Organisms might develop extraordinary radiation resistance, diverse photosynthetic mechanisms, and profound adaptations to extreme conditions, offering a vivid, albeit speculative, picture of life's resilience and versatility in the universe. Impacts from celestial bodies have played a paradoxical yet pivotal role in the origin and evolution of life on Earth and potentially elsewhere in the universe. On one hand, impacts can be highly destructive, causing mass extinctions and dramatic shifts in the environment. The most renowned example is the asteroid impact around 66 million years ago, which led to the extinction of the dinosaurs and paved the way for mammals and eventually humans to become dominant. This event, known as the Cretaceous-Paleogene (KPG) extinction, caused global wildfires, a nuclear winter, and acid rain, dramatically altering ecosystems and forcing rapid evolutionary changes. On the other hand, impacts have also been creative forces, possibly contributing to the origin of life itself. The early solar system was a chaotic place, with frequent collisions known as the Late Heavy Bombardment around 4 billion years ago. These impacts could have delivered essential organic compounds, including amino acids and nucleotides, the building blocks of life, to the early Earth. Some theories even suggest that life's precursor molecules formed in the harsh conditions of space and were transported to Earth by comets and meteorites, a concept known as panspermia. Evidence for this includes the discovery of organic molecules in extraterrestrial objects like the Murchison meteorite. Impacts might have also created habitats favorable for the origin of life. The intense heat and pressure from collisions can produce hydrothermal systems, similar to those found at Earth's deep ocean vents today, where many scientists believe life may have begun. These systems offer rich chemical environments and energy sources in the form of thermal gradients and mineral-rich fluids, potentially creating the perfect crucible for life to emerge. Additionally, craters from impacts can become warm, water-filled basins, providing stable environments where prebiotic chemistry could progress towards life. In evolutionary terms, impacts serve as catalysts for change. By disrupting existing ecosystems, they create evolutionary bottlenecks where only the most adaptable species survive, leading to bursts of diversification and the emergence of new species. The post-impact world is often a drastically different place, fostering rapid evolutionary experimentation and innovation. For instance, following the KPG extinction, the adaptive radiation of mammals led to the development of diverse forms and ecological niches that were previously dominated by dinosaurs. While impacts undoubtedly pose a significant threat, they are also integral to the dynamism of life's narrative. Their dual role as both destructors and facilitators underscores the complexity and resilience of life's journey, providing crucial opportunities for both the emergence of new species and the adaptation of existing ones to ever-changing environments. This intricate interplay between destruction and creation continues to shape not only our planet, but also offers a window into how life might evolve in other parts of the cosmos. Searching for techno-signatures, which are indicators of advanced extraterrestrial technologies, expands the scope of the quest for alien life beyond biological markers. Several promising methods and strategies have been proposed and are currently under investigation to identify these signs of technologically advanced civilizations. One primary method involves radio astronomy, which has been employed for decades, famously exemplified by projects like the search for extraterrestrial intelligence. Radio telescopes scan vast swathes of the sky for non-random, narrow-band radio signals that could signify artificial origin, such as those intentionally sent as interstellar beacons. Natural astrophysical processes generally produce broad-spectrum noise, so a narrow-band signal can stand out as a potential techno-signature. With advancements in technology, the capability of detecting these signals has improved, enabling the monitoring of millions of frequencies simultaneously over large sections of the sky. The Breakthrough Listen initiative, for example, is a contemporary effort leveraging state-of-the-art equipment to listen for such signals across a broader range of frequencies and a larger number of star systems. Another intriguing approach focuses on detecting laser emissions. Lasers can produce very detectable, coherent light beams that could be used by advanced civilizations for communication or even as part of propulsion systems for spacecraft. Instruments like high-resolution optical telescopes can be adapted to search for these concentrated light pulses in visible or infrared spectra. Lasers would appear as strong, monochromatic signals against the background of natural starlight, making them relatively easier to identify with the right equipment. The search for techno-signatures also extends to possible alterations of planetary environments and structures at a large scale. For instance, the detection of megastructures such as Dyson spheres, hypothetical constructs that encapsulate a star to harness its energy, could indicate advanced technological capabilities. Observational strategies might look for unusual stellar dimming patterns or plan to analyze the infrared signatures that such structures might emit. The anomalous dimming of Tabby's star, Chi C8462852, brought attention to this possibility, although natural explanations have since been proposed. Additionally, we can look for pollution as a techno-signature. Advanced civilizations might produce industrial pollutants detectable in their planetary atmospheres. Molecules not typically found in natural processes, such as certain chlorofluorocarbons, CFCs, could be detected through spectroscopic analysis of exoplanetary atmospheres. This method requires extremely sensitive instruments and is an area of great interest, particularly with the advent of powerful space-based observatories like the James Webb Space Telescope, JWST. Lastly, artificial satellites or space debris in orbit around distant planets could serve as techno-signatures. High-resolution imaging of extrasolar systems might reveal non-natural objects reflecting or emitting radiation in characteristic ways. This approach would require instruments capable of discerning small, high-contrast objects close to distant stars, a considerable technological challenge, but within the realm of future advancements. Together, These methods create a robust framework for the search for technosignatures. The ongoing development in telescopic capabilities, computational power for signal processing, and international collaborations bolster the likelihood of detecting signs of advanced extraterrestrial civilizations if they exist and are emitting detectable technosignatures. Discovering extraterrestrial microbial life would have profound implications across multiple domains, from science and philosophy to society and religion. Firstly, such a discovery would revolutionize our understanding of biology and the origin of life. If microbial life exists elsewhere in the universe, it suggests that life is not a unique phenomenon confined to Earth. This would imply that life could be common throughout the cosmos, just requiring the right conditions to thrive. Such a finding could significantly advance astrobiology by providing new models of biochemistry, potentially demonstrating alternate forms of life that operate under different environmental conditions and with different molecular building blocks from those on Earth. From a scientific perspective, finding extraterrestrial microbial life could offer insights into the adaptability and resilience of life forms. It would raise questions about the potential for panspermia, the hypothesis that life can spread from one planet to another through space debris. If the biochemistry of extraterrestrial microbes closely resembles that of terrestrial organisms, it might suggest a shared origin, whereas distinct biochemical processes could indicate independent genesis events. The study of their genetic and metabolic pathways could lead to groundbreaking advancements in biotechnology, medicine, and even theories of life's evolution. Philosophically, the discovery of extraterrestrial life would challenge anthropocentric views of our place in the universe. It would prompt a reassessment of humanity's uniqueness and the notion of life's purpose. This could foster a more universal perspective, emphasizing the commonality of life as a cosmic phenomenon. Religious and cultural implications would vary. Some traditions might find such a discovery in harmony with their teachings, seeing it as an affirmation of life's pervasiveness, while others might need to reconcile this new knowledge with their existing worldviews. The societal ramifications are equally significant. How we perceive and interact with our environment and each other could shift as humanity absorbs the knowledge that we are not alone. There would be ethical considerations regarding the protection and study of extraterrestrial microbes. Ensuring that we do not contaminate other worlds with Earth-based organisms or vice versa would become even more critical, raising the bar for planetary protection protocols. Legislations and policies regarding space exploration and the ethical treatment of alien biospheres would need to be established or revised. Moreover, the discovery could have practical implications for future space exploration and colonization. Understanding how life survives and thrives in extraterrestrial environments could inform the search for habitable zones on other planets, guiding future missions and potentially influencing the design of life support systems for long-term human settlements. It might also inspire a surge in scientific interest and funding, igniting a new era of enthusiasm for space exploration and research. Overall, the implications of finding extraterrestrial microbial life are vast and far-reaching, touching every aspect of human endeavor and thought. The discovery would mark a monumental milestone in our quest to understand the universe and our place within it, potentially unifying humanity in a shared sense of curiosity and awe. Planetary habitability is a dynamic quality that can change significantly over time, influenced by a range of astronomical, geological, and biological processes. One of the primary drivers of habitability is stellar evolution. A star's luminosity and activity evolve over its life cycle, impacting the habitable zone, the region around a star where conditions might be right for liquid water to exist. For instance, as our sun ages, it gradually becomes brighter and hotter. Over billions of years, this increasing luminosity will shift the habitable zone outward. Earth, currently within the habitable zone, will eventually face conditions that make it inhabitable as surface temperatures rise and oceans evaporate. Another critical factor is planetary geology, particularly tectonic activity. Tectonics play a vital role in regulating a planet's climate through the carbon silicate cycle, a natural thermostat that controls atmospheric carbon dioxide levels over geological timescales. This cycle involves the weathering of rocks, which pulls carbon dioxide out of the atmosphere, and volcanic activity, which releases it back. A planet without tectonic activity could find its atmosphere and climate becoming unstable, either freezing over or overheating. Mars, for example, may have had habitable conditions in its past when it had active volcanism and liquid water, but became a cold, dry planet as its interior cooled and tectonic activities ceased. The presence and evolution of a planet's magnetic field also significantly impact habitability. A strong magnetic field protects the planet from solar and cosmic radiation, which can strip away the atmosphere and degrade the surface environment. Earth's magnetic field shields it from harmful solar winds, a protection that may have allowed life to flourish. In contrast, the loss of Mars's magnetic field is believed to have contributed to the thinning of its atmosphere and the loss of its surface water. Biological activity itself can alter planetary habitability. Life forms, especially microorganisms, significantly impact atmospheric composition and surface conditions. On Earth, the emergence of photosynthetic bacteria led to the Great Oxygenation Event around 2.4 billion years ago, dramatically increasing atmospheric oxygen and paving the way for complex life. Similarly, methane-producing organisms could influence atmospheric greenhouse gas levels elsewhere, impacting surface temperatures and chemistry. Finally, catastrophic events such as asteroid impacts, volcanic supereruptions, and nearby supernova can reset the habitability conditions of a planet abruptly. Such events can cause mass extinctions, climate changes, and atmospheric loss. The Chicxulub impact, which contributed to the extinction of the dinosaurs, also reset Earth's ecosystems and allowed mammals to become dominant, thereby reshaping the path of evolution and habitability. Overall, the habitability of a planet is not a static attribute, but a dynamic interplay of astrophysical, geological, and biological factors evolving over significant timescales. Understanding these processes helps guide our search for habitable exoplanets and informs us about the long-term potential for sustaining life, both on Earth and beyond. Extremophiles, organisms that thrive in extreme conditions, offer valuable insights into the potential existence and nature of alien life. These resilient life forms extend our understanding of the limits of life, demonstrating that biological creatures can adapt to conditions previously thought to be inhospitable. Studying extremophiles helps scientists formulate hypotheses about the types of environments where life might exist beyond Earth and the biochemical adaptations that could support it. Take, for instance, thermophiles and hyperthermophiles, which flourish in extremely high-temperature environments such as hydrothermal vents on the ocean floor. These organisms thrive at temperatures exceeding 100 degrees Celsius, some even up to 121 degrees Celsius. The study of their unique protein structures and enzyme systems, which remain stable and functional at such high temperatures, suggests that similar life forms could exist in the subsurface oceans of icy moons like Europa and Enceladus, where geothermal activity might provide analogously hot environments. Similarly, psychrophiles, which live in freezing temperatures, show that life can persist even in environments as cold as -20 degrees Celsius or lower. These organisms produce antifreeze proteins and adaptable cell membranes that prevent ice crystal formation, allowing them to survive in cold environments such as the polar ice caps and deep, icy ocean trenches. This adaptability bolsters the argument for potential microbial life on Mars' polar ice caps, or under the icy crust of Triton, Saturn's largest moon, where such adaptations could be critical for survival. Halophiles, which thrive in highly saline environments, illustrate how life could adapt to extreme salinity. These organisms manage high salt concentrations by maintaining osmotic balance through specialized cellular mechanisms. The presence of briny subsurface lakes on Mars, indicated by radar data, could be habitats for similar salt-loving organisms, suggesting that life on Mars, if it exists, might be adapted to highly saline conditions. Another fascinating group is acidophiles and alkalophiles, which can live in highly acidic or alkaline environments, respectively. These extremophiles maintain internal pH stability through highly efficient proton pumps and other cellular mechanisms. Such organisms offer models for life on planets or moons with extreme pH conditions, such as the acidic clouds of Venus or the alkaline hydrothermal vents potentially found on other ocean worlds. Lastly, extremophiles known as radio-resistant organisms, such as Deinococcus radiodurans, can withstand extreme radiation levels. These organisms have efficient DNA repair mechanisms, allowing them to thrive despite intense radiation that would be lethal to most life forms. This resilience suggests that life could exist on planets and moons with thin atmospheres and high levels of cosmic radiation, such as the surface of Mars or even within Europa's icy crust if radiation from Jupiter penetrates it. By studying extremophiles on Earth, we gain invaluable clues about the potential biochemical versatility and adaptability of life in the universe. These insights shape our search strategies for extraterrestrial life, guiding the design of experiments and instruments in space missions to detect biomarkers and assess habitability. The remarkable adaptability of extremophiles underscores the profound possibility that life could exist in a myriad of forms and environments far beyond our terrestrial expectations, expanding our understanding of life's potential in the cosmos. Communicating with intelligent extraterrestrial life, should we encounter it, presents a complex and fascinating challenge. The process would require overcoming significant linguistic, cultural, and technological barriers. Initial contact would likely rely on the transmission and reception of electromagnetic signals, similar to the methods used in the search for extraterrestrial intelligence programs. These programs typically focus on detecting artificial radio or laser signals, which could serve as potential indicators of advanced civilizations. The first step in communication would involve establishing the presence and intentionality of a signal. A coherent, repetitive, or mathematically structured message would suggest an artificial origin. Mathematics, being a universal language, might serve as the initial foundation for communication. Simple mathematical sequences like prime numbers, the Fibonacci series, or basic arithmetic could demonstrate the existence of intelligent life and form the basis for further dialogue. The Arecibo message, transmitted in 1974, exemplifies this approach. It contained basic information about human biology, our solar system, and DNA structure using binary coding and graphical representations. Once a signal is confirmed as coming from intelligent extraterrestrial life, the next step would be attempting to decipher and respond to it. This requires creating a shared understanding of symbols and concepts. Visual or pictorial representations accompanying numerical data might help bridge linguistic gaps. These could illustrate basic physical principles, planetary systems, or even biological forms. For example, using images to convey universally understood concepts such as stars, planets, or simple geometric shapes might foster common ground. Language construction for extraterrestrial communication would need to adhere to principles of semiotics, ensuring that the symbols and syntax used are interpretable. The development of a lingua cosmica, or linkos, a proposed universal language for cosmic communication, would involve creating messages that build complexity gradually, starting from simple and easily understandable concepts, moving to more intricate ideas. This approach assumes that intelligent beings would have the cognitive ability to interpret such constructions logically. Beyond the initial exchange, sustained communication would necessitate mutual learning and adaptation. Interactive, real-time communication is unlikely due to the vast distances involved, so messages and responses would be sent across potentially long periods, taking years or even decades to travel between civilizations. This slow interchange requires questions and answers to be formulated with patience and foresight, anticipating the cooperative learning process needed to bridge the immense cultural and cognitive gaps. Ethical considerations also play a significant role. The content of our messages, and the decision to respond at all, would need careful deliberation within the global community, focusing on the potential consequences of such a monumental interaction. Ensuring that any communication does not inadvertently convey hostility, imperialism, or misunderstanding is crucial. The involvement of diverse cultures and perspectives in shaping these messages would be necessary to represent humanity authentically and responsibly. Communicating with intelligent extraterrestrial life would involve initial signal recognition, establishing common linguistic and mathematical ground, sending and decoding structured messages, and addressing substantial ethical concerns. It requires global cooperation, a careful and methodical approach, and an openness to learning from potentially very different forms of intelligence. The process would mark a profound milestone in our understanding of the universe and ourselves. Stars are born in the large, cold regions of space known as molecular clouds, clouds so dense and cool that hydrogen atoms pair up to create molecules. These clouds often span light years across and hold enough gas and dust to form thousands of new stars. Within these stellar nurseries, the process of star formation begins when certain conditions cause sections of the cloud to become unstable and start to collapse under their own gravity. Imagine a peaceful, foggy morning suddenly stirred by a gust of wind. Much in the same way, external forces such as shock waves from nearby supernova or the gravitational influence of passing objects can compress regions within a molecular cloud. When this compression occurs, the temperature within the collapsing region begins to rise, creating what we call a protostar. The process is governed by the principles of thermodynamics and gravitational physics. As the gas molecules fall inward, they convert gravitational potential energy into heat, causing the core to become increasingly hot and dense. Over the span of millions of years, if the protostar gathers enough mass, reaching a temperature of around several million degrees, nuclear fusion ignites. Hydrogen atoms in the core fuse together to form helium, releasing a phenomenal amount of energy and marking the birth of a new star. This transformation from a cold lump of dust and gas to a blazing stellar beacon is one of the most awe-inspiring phenomena in the universe, governed by laws of physics that connect the cosmic to the tiniest atomic scales. The stunning shapes and vivid colors observed in planetary nebulae are a cosmic encore, playing out the final acts of dying stars like our Sun. Imagine a serene, aging actor withdrawing from a grand stage, leaving behind a legacy of complex emotions and stories. Similarly, as a star exhausts the nuclear fuel in its core, it becomes unstable, expelling its outer layers into the surrounding space. This ejected material forms the nebula, a glowing shell of gas and dust showcasing a myriad of shapes like rings, spirals, or even intricate symmetrical patterns resembling cosmic flowers. The forces responsible for these shapes are multifaceted. Stellar winds, streams of charged particles emitted from the dying star, sculpt the nebula into intricate forms, while magnetic fields and binary star systems introduce further complexity and symmetry to these celestial artworks. The dazzling colors of planetary nebulae arise from the interaction of ionized gas with ultraviolet radiation from the hot core of the dying star. Different elements emit light at specific wavelengths when ionized, producing the spectacular array of colors we observe. For instance, ionized hydrogen shines red, while oxygen ions emit a striking greenish-blue hue. These glowing gases are not just a pretty show, they provide a rich tapestry of information about the composition and dynamics of the dying star's life. The interplay of these elements, influenced by the star's mass, composition, and the presence of nearby companions, results in the enchanting and diverse structures we observe through telescopes. These nebulae serve as both a spectacular end and a fertile beginning, as the expelled materials will eventually coalesce to form new stars, planets, and possibly even life, continuing the infinite cycle of cosmic evolution. Supernova remnants are the spectacular leftovers from one of the universe's most powerful events, the explosive death of a massive star. When a star that is at least 8 times more massive than our Sun depletes its nuclear fuel, its core collapses under gravity, triggering a supernova explosion that can outshine an entire galaxy for a brief time. The force of this explosion ejects the star's outer layers into space at speeds reaching up to 30,000 kilometers per second, forming a supernova remnant. These remnants, initially a chaotic mix of high-energy particles and radiation, evolve over thousands of years, interacting intricately with the interstellar medium, the sparse mixture of gas and dust that fills the gaps between stars. Immediately after the explosion, the shock wave from the supernova travels outward, sweeping up surrounding material and compressing it to incredibly high temperatures and densities. This shockwave can trigger the formation of new stars by compressing nearby molecular clouds, essentially seeding the next generation of stellar nurseries. Over time, the ejected material slows down and cools, but the energetic process continues to be a cosmic recycling plant, enriching the interstellar medium with heavy elements such as iron, oxygen, and silicon. These elements originated in the core of the progenitor star and are crucial for forming planets and organic molecules. Thus, supernova remnants play a pivotal role in cosmic evolution, driving the creation of new stars and influencing the chemical makeup of future solar systems. Through their dynamic and far-reaching interactions, these remnants weave an intricate narrative of destruction and renewal in the mind-bendingly large tapestry of the universe. Interstellar dust, the seemingly insignificant tiny particles scattered throughout the cosmos, plays a monumental role in the formation of planets. These minuscule grains, often composed of silicates, carbon compounds, and ice, are the building blocks of planetary systems. Imagine a vast cosmic bakery where dust grains serve as the flour from which the loaves of planets are eventually baked. Within molecular clouds, these dust particles act as raw material, facilitating the cooling processes necessary for the collapse of gas clouds to form stars and their accompanying protoplanetary disks. As a new star begins to form, its surrounding disk, composed of gas and interstellar dust, undergoes a fascinating transformation. Dust grains within this protoplanetary disk collide and stick together through electrostatic forces, gradually coalescing into larger particles. Over time, these particles continually clump, forming planetesimals, which are essentially the seeds of future planets. The process is a bit like snowballing. As these planetesimals grow, their gravitational pull increases, attracting even more material and leading to the formation of protoplanets. This process eventually culminates in the creation of fully fledged planets, moons, and other small solar system bodies. Beyond serving as the foundational building blocks, interstellar dust also plays a critical role in chemical reactions essential for life. These dust grains act as catalysts, providing surfaces on which molecules can form and grow, including organic compounds which are the precursors to life. The dust shields these chemical processes from harmful stellar radiation by absorbing and scattering light, creating a protective, nurturing environment within the cold, dark regions of space. Thus, interstellar dust is not just a passive spectator, but an active participant in crafting the intricate and diverse planetary systems observed throughout our galaxy. Cosmic rays, those high-energy particles that zoom through space at nearly the speed of light, are like the invisible threads that weave through the fabric of the universe, interacting profoundly with the interstellar medium. These particles, primarily protons along with heavier atomic nuclei and electrons, originate from various energetic processes, including supernova explosions and active galactic nuclei. When cosmic rays collide with interstellar gas and dust, their incredible energy induces a cascade of interactions, igniting a rich tapestry of astrophysical processes that shape the galaxy's chemical, physical, and magnetic properties. One of the most vital roles cosmic rays play is in the ionization of the interstellar medium, particularly hydrogen atoms. When a cosmic ray crashes into a hydrogen atom, it strips away an electron, creating a positively charged ion. This ionization process not only alters the magnetic and thermal properties of the interstellar medium, but also serves as a catalyst for complex chemical reactions. For example, the formation of molecular hydrogen, the most essential molecule for star formation, is significantly accelerated by the ionization effects caused by cosmic rays. This, in turn, affects the cooling rates and dynamical evolution of molecular clouds, influencing where and when new stars will form. Furthermore, cosmic rays contribute to the thermal pressure within interstellar clouds. As these particles penetrate deep into the clouds, their interactions deposit energy, heating the gas and balancing gravitational collapse. This heating mechanism helps regulate the temperature of the interstellar medium, preventing it from cooling too quickly and collapsing prematurely. Additionally, cosmic rays play a role in shaping the magnetic fields of the galaxy. As they spiral along magnetic field lines, cosmic rays exert a force that can amplify and maintain these fields, contributing to the overall structure and stability of the interstellar medium. Through these dynamic interactions, cosmic rays are fundamental in sculpting the essence of the galaxy, playing a hidden yet vital role in its ongoing evolution. The intergalactic medium, IGM, serves as the vast ethereal expanse that lies between galaxies, occupying more than half of the universe's visible matter. Composed primarily of ionized hydrogen known as plasma, the IGM also includes helium and trace amounts of heavier elements such as carbon, oxygen, and nitrogen. The hydrogen exists mainly as single protons and electrons. ionized by the intense ultraviolet radiation from galaxies and quasars. This medium isn't a uniform expanse, but rather a complex web of filaments and voids, often described as the cosmic web, reflecting the large-scale structure of the universe. Structurally, the IGM is remarkably dynamic. Within this cosmic web, dense regions known as nodes mark the intersections where filaments converge, harboring galaxy clusters. These denser areas are rich in gas that can cool and condense to form new galaxies, playing a crucial role in galaxy formation and evolution. Meanwhile, the tenuous filaments act as highways for gas and dark matter, linking these nodes and fueling the growth of structures within the universe. Observations from instruments like the Hubble Space Telescope and the Chandra X-ray Observatory have revealed that the temperature in these filaments can range from a few thousand to millions of degrees Kelvin, with hotter regions typically associated with the shock waves generated by gravitational interactions and the formation of structures. This intergalactic plasma is not just passive filler, it actively participates in the cosmic ballet. The IGM serves as the reservoir from which galaxies draw material to sustain star formation, and it also acts as a sink for the energy and matter expelled by galaxies via winds and supernova. The interaction between galaxies and the IGM is a continuous feedback loop, influencing galaxy evolution across cosmic time. The presence of heavier elements in the IGM is a testament to this interaction, indicating that supernova explosions have propagated elements forged in stars into this vast medium, enriching it over billions of years. Thus, the composition and structure of the intergalactic medium are vital not only to understanding the distribution of matter in the universe, but also the intricate evolutionary pathways of galaxies themselves. HEI regions, those glowing clouds of ionized hydrogen surrounding newborn stars, are like celestial nurseries, profoundly shaping star formation in galaxies. These regions form around young, massive stars that emit copious amounts of ultraviolet radiation, capable of ionizing the hydrogen gas in their vicinity. The result is a luminous nebula that radiates light and heat, making these spots some of the most visually spectacular areas in galaxies. But beyond their beauty, HII regions are fundamental in both fostering and regulating the birth of new stars. The influence of HII regions on star formation is multifaceted. Firstly, the intense radiation from the young stars that power HII regions heats and ionizes the surrounding gas. This heating creates a high-pressure environment that can push against nearby molecular clouds, compressing them and triggering the gravitational collapse necessary for star formation. Essentially, the young stars act like cosmic catalysts, their radiation creating conditions that favor the birth of even more stars. This process, known as triggered star formation, can lead to waves of star birth propagating through a galaxy as each generation of stars initiates the formation of the next. However, the impact of HII regions isn't solely about nurturing new stars. The energy they release also acts as a form of feedback that can inhibit star formation in some areas. The powerful stellar winds and radiation from the massive stars can blow away the surrounding gas, dispersing the material needed to form new stars and creating cavities known as bubbles or superbubbles. In this sense, HII regions play a dual role. They can both stimulate star formation by compressing gas and curtail it by dispersing it. This balance between stimulating and suppressing star formation dictates the overall star formation rate within a galaxy, influencing its evolution. In this cosmic interplay, HII regions are crucial actors, regulating the rhythm of star birth and shaping the growth and structure of galaxies. Their influence extends beyond their immediate surroundings, impacting the interstellar medium's condition and thus setting the stage for the next stars to emerge. Through these processes, HII regions ensure that galaxies remain vibrant, dynamic systems, continuously evolving through cycles of star formation and feedback. The filamentary structure observed in some nebulae is a mesmerizing display of cosmic dynamics, resulting from a combination of physical processes that shape these intricate thread-like patterns. One primary factor in the formation of these filaments is the interaction of stellar winds and shock waves. Massive stars often emit strong winds that sweep through the surrounding gas, compressing it into elongated shapes. Imagine a powerful gust of wind creating ripples across a sandy beach. Similarly, these stellar winds carve out filaments in the interstellar medium. Additionally, shock waves from supernova explosions play a significant role in creating filaments. When a massive star reaches the end of its life and undergoes a supernova, it releases an enormous amount of energy, sending shock waves through the surrounding gas. These shock waves compress and heat the gas, generating high-pressure regions that form into elongated filaments and arcs. This process is particularly evident in supernova remnants, where the expanding shock wave continues to interact with the interstellar medium, perpetuating the formation of these structures over thousands of years. Magnetic fields also contribute to the filamentary appearance of nebulae. The interstellar medium is threaded with magnetic fields that can channel the movement of charged particles. As gas and dust interact with these magnetic fields, they tend to align along the field lines, creating filamentary structures. These magnetic forces can organize the gas and dust into elongated shapes, much like iron filings align themselves along the lines of a magnetic field on Earth. Finally, gravitational interactions and turbulence within molecular clouds can further enhance the filamentary structure. As regions within these clouds collapse under gravity to form new stars, the surrounding material gets pulled into filaments. At the same time, turbulent motions within the clouds can stretch and twist the gas into complex filamentary patterns. These combined effects, stellar winds, shock waves, magnetic fields, gravity, and turbulence, give rise to the stunning, intricate filaments we observe in nebulae, painting a dynamic and ever-changing picture of the cosmos. Interstellar magnetic fields play a profound role in sculpting the behavior of gas and dust within galaxies, exerting an unseen yet powerful influence on the movement and structure of cosmic matter. Imagine these fields as invisible scaffolding that guides the dance of particles in the interstellar medium. Magnetic fields, though typically weak compared to other forces in the universe, have a significant impact when it comes to the dynamics of the vast diffuse gas and fine dust spread throughout galaxies. Their influence begins with their ability to align and constrain the motion of charged particles. When gas, primarily composed of ions and electrons, encounters a magnetic field, the charged particles spiral around the magnetic field lines. This motion constrains the gas, inhibiting it from freely moving in directions perpendicular to the field lines and creating elongated structures that follow the magnetic lines of force. These magnetic fields also affect the process of star formation. In molecular clouds, where stars are born, magnetic fields can slow down the collapse of gas under gravity. This creates a balance with the gravitational force, leading to the formation of dense cloud cores from which stars can eventually form. The magnetic fields can provide support against gravitational collapse, regulating the rate at which stars are born and preventing all the gas from collapsing at once. This magnetic tension acts like a safety net, ensuring that star formation is a more gradual process, allowing new stars to form over extended periods rather than in a sudden burst. Furthermore, magnetic fields influence the turbulence within molecular clouds. Turbulence is a chaotic and erratic motion driven by various forces including gravity and supernova shock waves. Magnetic fields can organize and dampen this turbulence, leading to the creation of filamentary structures observed within the clouds. These filaments are often the sites where star formation occurs. Additionally, the interaction of magnetic fields with dust grains causes the grains to align with the magnetic fields, affecting the polarization of light that passes through the dust. This polarization provides astronomers with crucial information about the direction and strength of interstellar magnetic fields. Overall, interstellar magnetic fields are fundamental in shaping the movement and organization of gas and dust in the cosmos. By guiding the flow of charged particles, regulating star formation, and organizing turbulence, these magnetic fields contribute significantly to the structure and evolution of galaxies, painting an intricate and invisible backbone to the tapestry of the universe. Studying the various types of nebulae provides astronomers with critical insights into the complex processes of stellar evolution, offering a detailed narrative of a star's life cycle from birth to death. Each type of nebula captures a different phase in the life cycle of stars, revealing the underlying physical principles governing their formation, evolution, and eventual demise. Imagine each nebula as a chapter in a grand cosmic story, each contributing distinct pieces of information to our understanding of stellar phenomena. For instance, Star-forming regions known as HII regions and emission nebulae offer invaluable glimpses into the birth and early development of stars. These nebulae are rich in gas and dust, where young, hot, massive stars ionize the surrounding hydrogen, causing it to glow brightly. The study of HII regions allows scientists to observe the initial stages of stellar formation and understand how stars influence their environment through stellar winds and radiation. By analyzing these regions, astronomers can deduce how the process of triggered star formation works, where the radiation and winds from young stars compress nearby gas clouds, potentially giving rise to new stars. This knowledge helps us comprehend how stellar nurseries are scattered across galaxies and the conditions necessary for star formation to occur. On the other end of the stellar life cycle, planetary nebulae and supernova remnants provide deep insights into the final stages of stellar evolution. Planetary nebulae, which form when low to intermediate mass stars eject their outer layers as they run out of nuclear fuel, reveal details about the processes occurring during a star's dying phase. These glowing shells of ionized gas help us understand how stars return material to the interstellar medium, contributing to the chemical enrichment of future generations of stars and planets. Analyzing planetary nebulae enables astronomers to study the elemental abundances created during the star's lifetime, shedding light on nucleosynthesis, the process by which new atomic nuclei are produced. Supernova remnants represent the explosive deaths of massive stars and are key to understanding the most dramatic stellar ends. The shock waves from supernova explosions propagate through space, heating and compressing interstellar material and triggering new star formation events. Studying these remnants allows scientists to investigate the extreme conditions under which heavy elements are forged and dispersed across the cosmos, enriching the interstellar medium with elements like iron, gold, and uranium. These explosions also generate cosmic rays, contributing to high-energy processes in the galaxy. Reflection nebulae and dark nebulae also play vital roles in our understanding of how stars interact with their surroundings. Reflection nebulae, which shine by scattering the light of nearby stars, help us study the properties of interstellar dust and examine how light is affected as it traverses through space. Dark nebulae, which obscure light from background stars, offer insight into the densest regions of interstellar clouds, often serving as the birthplaces of new stars. By piecing together information from these various types of nebulae, astronomers can form a comprehensive picture of stellar evolution, tracing the journey of stars from their formation in dense molecular clouds to their ultimate fate as planetary nebulae or supernova remnants. This intricate tapestry of stellar life cycles enhances our understanding of the universe's history, contributing to our knowledge of galaxy evolution, star formation rates, and the cosmic enrichment of elements essential for life. Spiral arms in galaxies are fascinating structures, and their formation is primarily attributed to the density wave theory. This theory suggests that the spiral arms are not made up of a permanently fixed group of stars, but rather that they are areas of higher density that move through the galaxy, much like a traffic jam moves along a highway. As stars, gas, and dust enter these denser regions, they slow down and become more tightly packed, lighting up the spiral arms. These density waves trigger star formation, leading to the bright young stars that we see illuminating the arms, making them stand out against the darker backdrop of space. As for maintaining their shape, the spiral arms persist over time due to the differential rotation of the galaxy. The inner regions of a galaxy rotate faster than the outer regions. Without the density wave mechanism, the arms would wind up and lose their structure fairly quickly. However, the persistent gravitational effects and interactions, along with the density waves, help keep the arms stable. Additionally, gravitational influences from nearby galaxies or galactic bars can stimulate and regulate these spiral formations, ensuring they retain their majestic and recognizable shape across cosmic timescales. Stellar populations constantly refresh within these arms, maintaining their bright and distinct appearance as young, hot stars continue to be born and illuminate the paths through which these waves travel. Galactic bars are intriguing structures that are found at the center of about 2/3 of all spiral galaxies, and their development is closely linked to gravitational instabilities within the galactic disk. When stars and gas move within the rotating disk of a galaxy, small perturbations can grow due to gravitational interactions. Over time, these perturbations can amplify and stretch into the distinct elongated shapes that we recognize as bars. These bars are essentially regions where the density of stars and interstellar matter is higher. The presence of a bar can significantly affect the internal dynamics of a galaxy. Bars act as a mechanism to channel gas from the outer regions of the galaxy towards the center. This flow of gas can feed the central regions, potentially fueling star formation activity and even the growth of a central supermassive black hole. Studies have shown that bars can also act like engines driving the spiral structure by redistributing angular momentum within the galactic disk. The development of a bar can be a relatively rapid process in cosmic terms, sometimes forming in a few 100 million years. Over longer timescales, interactions with neighboring galaxies can also play a role, potentially triggering or enhancing bar formation through gravitational tidal forces. These dynamic processes illustrate how galaxies are not static entities, but are constantly evolving and reshaping themselves over time. Galactic interactions and mergers are among the most dramatic and influential events in the universe. These interactions begin long before the actual merging of galaxies, often starting with gravitational pulls that distort their shapes. As galaxies draw nearer, their mutual gravitational attraction leads to the formation of tidal tails, long, stream-like features of stars and gas that are pulled out from the galaxies. These gravitational forces can also compress gas within the galaxies, triggering bursts of star formation known as starbursts. Eventually, the galaxies can collide and merge, creating something altogether new. The consequences of such a merger are profound. As the cores of the galaxies come together, it often results in the formation of an elliptical galaxy, especially when two large spiral galaxies merge. The chaotic collision can drive gas towards the center, feeding central supermassive black holes and potentially triggering active galactic nuclei, which can outshine the entire galaxy for a period. The energy released during the merging process can heat up the gas, preventing it from cooling and forming new stars for a significant length of time. This is why many elliptical galaxies contain older stellar populations with little ongoing star formation. Over the span of millions to billions of years, the remnants of the merger settle into a new equilibrium, but the marks of their turbulent past are often preserved in the form of unusual stellar distributions, altered morphologies, and the presence of stellar streams. Such colossal cosmic events illustrate the dynamic and ever-changing nature of the universe. Galactic winds and outflows are driven primarily by intense star formation and the energetic processes associated with supermassive black holes, known as active galactic nuclei, AGN. In regions of rapid star formation, massive stars and supernova explosions release tremendous amounts of energy into their surroundings. This energy heats and expels gas at high velocities, creating powerful stellar winds. These winds can push material out of the galaxy, shaping its evolution by regulating the amount of gas available for future star formation. Essentially, the push from these explosive events acts as a feedback mechanism, preventing galaxies from growing too quickly and turning all their gas into stars prematurely. Active galactic nuclei also play a crucial role in driving galactic winds and outflows. When matter accretes onto a supermassive black hole, it releases an immense amount of energy in the form of jets and radiation. These energetic outputs can sweep up surrounding gas and drive it out of the galaxy. Active galactic nuclei-driven winds can reach velocities of several thousand kilometers per second, dispersing material far beyond the galactic boundaries. This process can have significant consequences, such as quenching star formation by blowing away star-forming gas and altering the intergalactic medium. These AGN activities ensure that galaxies do not consume all their gas too quickly, maintaining a balance that influences their long-term evolution. The interplay between stellar-driven winds and AGN activity thus acts as a self-regulatory mechanism, crucial for the life cycle of galaxies and their ability to form stars over cosmic timescales. Supermassive black holes profoundly influence the evolution of their host galaxies through a variety of mechanisms, primarily involving energetic feedback processes. Located at the centers of most large galaxies, these black holes can affect their surroundings through their immense gravitational pull and the release of vast amounts of energy when they accrete matter. This energy output can heat the surrounding gas and even eject it from the galaxy, a process known as active galactic nucleus feedback. AGN feedback can come in the form of powerful jets, intense radiation, and winds that sweep through the galaxy, thereby influencing star formation rates. By regulating the amount of cold gas available for new stars, supermassive black holes can effectively control the growth and evolution of their host galaxies. One significant consequence of AGN feedback is the prevention of runaway star formation. Without this feedback, galaxies could rapidly consume their gas reservoirs, forming stars at an unsustainable rate. The outflows generated by AGNs can push this gas out to the outer regions or even into interstellar space, maintaining a balance that allows galaxies to form stars over longer timescales. Additionally, the energy released can heat the gas, making it difficult for it to cool and condense into new stars. This is often observed in massive elliptical galaxies where star formation has been quenched, and most of the stars are older. Moreover, the interaction of these jets and winds with the surrounding environment can lead to the creation of shock waves and turbulence, further influencing the distribution and state of gas within the galaxy. Essentially, supermassive black holes act as a regulatory agent, ensuring that the processes within the galaxy occur in a balanced manner, thus shaping the galaxy's structure and future evolution. Galaxies that stop forming stars, often referred to as red and dead, undergo significant transformations due to a variety of processes that expel, compress, or heat the gas necessary for star formation. One primary mechanism behind this quenching of star formation is the feedback from active galactic nuclei, AGN. When a supermassive black hole at the galaxy's center accretes matter, it releases immense amounts of energy in the form of radiation and powerful jets. This AGN feedback can heat the surrounding gas to temperatures where it cannot cool down to form new stars, or can eject it entirely out of the galaxy, thereby depleting the galaxy's star-forming material. Another contributing factor is environmental effects in galaxy clusters. Galaxies in these dense cosmic neighborhoods can be subjected to processes like ram pressure stripping, where the hot, dense intracluster medium sweeps away the galaxy's gas as it moves through the cluster. Additionally, gravitational interactions with other galaxies, such as mergers and tidal forces, can trigger starbursts that rapidly consume the available gas. Post-starburst, the remaining gas may be too hot or too dispersed to coalesce into new stars efficiently. Over time, the galaxy exhausts its gas reservoir, and ongoing star formation grinds to a halt. The existing stellar population ages, with longer-lived, redder stars becoming dominant, giving these galaxies their characteristic red and dead appearance. A combination of internal mechanisms like AGN activity and external influences from the galaxy's environment work together to quench star formation, guiding the galaxy toward a more quiescent phase in its evolutionary journey. Dwarf galaxies, the smaller and less luminous cousins in the galactic family, form and evolve through a combination of internal processes and interactions with larger galaxies. Typically, dwarf galaxies have lower masses and weaker gravitational fields, which means they are more susceptible to external influences. Their formation often begins in the early universe, nearly 13 billion years ago, from small perturbations in the primordial gas. These perturbations collapse under gravity to form dwarf galaxies, which initially consist of dark matter halos, gas, and newly formed stars. Their limited gravitational pull can result in lower efficiencies in star formation, often leaving them with relatively large reservoirs of gas compared to their stellar content. The evolution of dwarf galaxies is strongly influenced by their larger companions. When a dwarf galaxy orbits a larger galaxy, tidal forces exerted by the larger galaxy can distort and strip material from the dwarf. This process, known as tidal stripping, can lead to the disruption of the dwarf galaxy's structure, pulling stars and gas into elongated streams that become part of the larger galaxy's halo. Additionally, ram pressure stripping can occur as a dwarf moves through the hot, diffuse gas in a galaxy cluster or the larger galaxy's halo, sweeping out the interstellar medium and quenching star formation. However, these interactions are not solely destructive. They can also trigger bursts of star formation by compressing the gas within the dwarf galaxy. Over time, many dwarf galaxies can be assimilated entirely by their larger counterparts, contributing stars and gas to the halos and disks of the more massive galaxies, as evidenced by stellar streams and other remnants observed around the Milky Way and other giant galaxies. This intricate ballet of interactions helps to shape both the dwarf galaxies and their larger companions, influencing the broader structure and evolution of the cosmic landscape. High-velocity clouds, HVCs, are fascinating components of the galactic halo, moving at speeds significantly different from the normal rotation of their host galaxies. The origin and nature of these clouds are varied and complex, catering to a range of astrophysical phenomena. One primary hypothesis suggests that HVCs are remnants of the primordial gas from which galaxies formed. These ancient gas clouds may have remained relatively unchanged over billions of years, serving as reservoirs of primordial hydrogen. Another theory posits that HVCs are the result of gas stripped from satellite galaxies during their interactions with a larger galaxy. These tidal interactions can pull gas out of the smaller galaxies, creating streams or clouds of gas that travel through the galactic halo. Additionally, high-velocity clouds can originate from galactic fountains, a process driven by intense stellar activity within a galaxy. Supernova explosions and strong stellar winds can expel gas from the galactic disk into the halo, where it cools, slows down, and eventually falls back towards the disk, creating a cyclic flow of material. This gas is enriched with heavy elements from the stellar processes, contributing to the chemical evolution of the galaxy when it reintegrates into the disk. The study of HVCs offers critical insights into the life cycle of baryonic matter in galaxies. These clouds can fuel star formation by delivering fresh gas back into the galactic disk. Observations using radio telescopes, particularly in the 21-centimeter line of hydrogen, provide valuable data on the velocities, compositions, and distributions of these clouds. Their interaction with the interstellar medium and the potential role they play in galactic evolution make them key elements in understanding the broader dynamics of galaxies. Galaxies acquire and retain their gas over cosmic time through an intricate interplay of cosmic accretion, intergalactic interactions, and internal recycling processes. The initial supply of gas for a galaxy typically comes from the accretion of intergalactic material. In the early universe, as structures began to form from the primordial soup of mostly hydrogen and helium, gas coalesced under gravity to form the first generation of stars and galaxies. Cold gas from the cosmic web continuously feeds these nascent galaxies, providing the necessary fuel for ongoing star formation. This inflow of gas is essential for the growth and sustainability of galaxies over billions of years. However, retaining that gas poses its own set of challenges. Internal processes such as star formation and supernova explosions generate significant amounts of energy, which can heat up the gas and even expel it from the galaxy. Supermassive black holes at galactic centers can also influence their host galaxies through active galactic nucleus (AGN) feedback, which can either heat the gas to prevent it from cooling and forming new stars or eject it altogether. Nonetheless, galaxies can also recycle gas through galactic fountains. In this process, supernova explosions and stellar winds blow gas out of the galactic disk into the halo, where it cools and eventually falls back into the disk, potentially triggering new star formation. Interactions with other galaxies and the intergalactic medium also play a crucial role. Minor mergers with smaller galaxies can deliver fresh gas supplies, rejuvenating star formation. On the other hand, in dense environments like galaxy clusters, galaxies can lose gas through ram pressure stripping, where the intergalactic medium sweeps away the gas as galaxies move through the cluster. Despite these losses, the interplay between gas inflows, recycling, and the complex dynamics of intergalactic interactions ensures that galaxies can sustain themselves and evolve in a universe that's constantly in flux. The diverse morphologies of galaxies, ranging from the elegant spirals to the more amorphous ellipticals, result from a combination of their initial conditions, their evolutionary histories, and their interactions with other galaxies and the intergalactic environment. The conditions present during a galaxy's formation, such as the distribution of dark matter, the density of the surrounding environment, and the dynamics of gas accretion, play foundational roles in determining its initial shape and structure. For instance, Spirals generally form in less dense environments where gas can settle into rotating disks, leading to their distinct flat disc-like shapes with ongoing star formation that illuminates their spiral arms. On the other hand, ellipticals often form through more violent processes. One of the leading scenarios for elliptical galaxy formation is the major merger hypothesis. When two or more spiral galaxies collide and merge, the gravitational chaos can strip stars from their orderly orbits, leading to the random spheroidal stellar distributions characteristic of elliptical galaxies. During these mergers, gas within the colliding galaxies can be compressed, triggering intense bursts of star formation, but this gas is often rapidly consumed or expelled by supernova explosions and AGN feedback. The result is a population of older, redder stars with little remaining cold gas to fuel new star formation, giving ellipticals their smooth, reddish appearance. Environmental factors also shape galaxy morphology. In dense regions like galaxy clusters, interactions and mergers are more common, leading to a higher proportion of elliptical and lenticular galaxies. Conversely, in less crowded areas, spiral and irregular galaxies are more prevalent. Smaller irregular galaxies often owe their chaos to gravitational interactions or accretion of varying-sized gas clouds that disrupt their shapes, while dwarf galaxies might exhibit any of these morphologies depending on their own particular history and interactions. Overall, a galaxy's path through cosmic history, shaped by its initial conditions, internal dynamics, and external interactions, orchestrates the vast variety of galactic forms we observe today.